time dilation. A fascinating and often mind-boggling aspect of Albert Einstein's theory of relativity occurs when an object approaches the speed of light, causing time to pass more slowly for it compared to an observer at rest. This phenomenon directly challenges our everyday, intuitive perceptions of a universal, constant flow of time. For instance, imagine a futuristic spaceship traveling at a significant fraction of the speed of light, while the astronauts aboard experience time in a perfectly normal, linear fashion. Observers back on Earth would notice something extraordinary. From their perspective, the clocks on the spaceship, and indeed every physical and biological process, would appear to be moving in slow motion. This creates a sort of cosmic time difference, a discrepancy in the experienced duration of events between the two reference frames. The effect becomes more pronounced, more dramatic, the closer the spaceship gets to the ultimate cosmic speed limit. This leads to scenarios that have long been the staple of science fiction, but which are grounded in real, physical theory. Astronauts could embark on a journey that, to them, feels like a few years, only to return to Earth and find that decades, or even centuries, have passed. Their friends and family would be long gone, the world they left behind a distant historical memory. It is a one-way ticket to the future, a journey where the price of speed is a profound and irreversible disconnection from the temporal stream of their home world. One of the most intriguing aspects of time dilation is its deep and intimate connection to the very fabric of spacetime and the presence of mass, according to Einstein's later and more comprehensive theory, general relativity. Time is not just affected by velocity, it is also affected by gravity. Time runs slower in stronger gravitational fields. So, if a spaceship were to travel near a massive, compact object like a neutron star or a black hole, the astronauts aboard would experience time at a different, slower rate than those far away from the object's immense gravitational influence. The event horizon of a black hole, the point of no return, is a place of extreme time dilation. An observer hovering just outside this boundary would experience time at an incredibly slow rate compared to a distant observer. If you were to orbit a black hole for what felt like a few hours, you could potentially return to your home base to find that centuries had passed. This is not just a theoretical curiosity. It is a real physical effect that has profound implications for our understanding of the cosmos. It tells us that time is not a universal metronome, ticking at the same rate for everyone and everything. It is a local, personal, and malleable phenomenon, a river that can flow at different speeds in different parts of the universe, its current shaped by the interplay of motion and gravity. These scenarios open up exciting, if daunting, possibilities for future space travel, but they also raise deep and complex questions about the nature of aging, of memory, and of the very definition of a human lifespan in the vast and relativistic tapestry of the cosmos. When considering the practical implications of time dilation for human space exploration, one must confront the immense technological hurdles that stand between our current capabilities and the dream of relativistic travel. The spacecraft we have built so far, like the Voyager probes which are now venturing into interstellar space, travel at speeds that are a tiny, almost infinitesimal, fraction of the speed of light. At these speeds, the effects of time dilation are real, but they are so small as to be completely negligible for the human experience, amounting to a time difference of mere seconds over a multi-decade journey. To make time dilation a significant factor, to turn it into a practical, if paradoxical, form of time travel, we would need to develop propulsion systems that are far beyond anything we can currently build. Scientists and engineers are, however, exploring a number of advanced and often highly speculative concepts that could one day allow us to approach these relativistic speeds, antimatter engines, which would work by annihilating matter and antimatter to release an incredible amount of energy, are one such possibility. Solar sails, vast ultra-thin mirrors that would be pushed by the pressure of sunlight itself, could over a long period of time accelerate a small probe to a significant fraction of the speed of light. And more exotic concepts, like fusion rockets or laser-propelled nanocraft, are also being actively researched. If we could one day build a spacecraft that could reach, say, 10% of the speed of light, a speed that is still far from the ultimate limit, but is vastly greater than anything we can achieve today, the effects of time dilation would become a noticeable and important part of the mission. The crew's clocks would run about 0.5% slower than the clocks on Earth. Over a 10-year mission, this would amount to a time difference of about 3 weeks. It is not a dramatic, science fiction-style leap into the future, but it is a real, measurable, and profound demonstration of one of the deepest and most beautiful truths of our universe, that time itself is relative. The famous twin paradox is not a true paradox in the logical sense, but is rather a powerful and beautifully clear thought experiment that is designed to illustrate the seemingly paradoxical, but physically real, consequences of time dilation. The scenario is a simple one. One of two identical twins embarks on a high-speed, round-trip journey into space, while the other twin remains on Earth. According to the principle of special relativity, the traveling twin, who is moving at a significant fraction of the speed of light, will experience time more slowly than their Earth-bound sibling. When the traveling twin returns to Earth, they will find that they are now biologically younger than their twin. The paradox arises when you try to apply the principle of relativity symmetrically. The traveling twin could argue that, from their perspective, it was the Earth that was moving away from them at a high speed, and therefore it should be the Earth-bound twin who is younger. This apparent contradiction is resolved by recognizing that the situation is not, in fact, symmetrical. The traveling twin has to accelerate to leave the Earth, turn around at their destination, and then decelerate to return. The Earth-bound twin, on the other hand, remains in a single, inertial frame of reference for the entire duration. It is this asymmetry, this breaking of the relativistic symmetry by the process of acceleration, that resolves the paradox and makes the traveling twin the definitively younger one upon their return. This is not just a hypothetical, abstract situation. It is a real physical effect that has tangible consequences in our modern technological world. The global positioning system, which our society now relies on for everything from navigation to financial transactions, would not work without a precise understanding and application of the principles of both special and general relativity. The GPS satellites are in orbit around the Earth, moving at high speeds and in a weaker gravitational field than we are on the surface. Both of these effects, the velocity-based time dilation of special relativity and the gravity-based time dilation of general relativity, cause the atomic clocks on the GPS satellites to tick at a slightly different rate than the clocks on the ground. If these relativistic effects were not precisely accounted for, the GPS system would accumulate errors of several kilometers per day, making it completely useless. The twin paradox, and the reality of time dilation it illustrates, is a powerful reminder that the universe does not always operate according to our common sense, terrestrial intuition. It is a universe where time is not a universal constant, but a personal and profoundly relative experience. Time dilation, the strange and beautiful phenomenon where time can pass at different rates for different observers, is one of the most profound and well-tested consequences of Albert Einstein's theory of relativity. It is a concept that fundamentally reshaped our understanding of space and time, revealing them to be not separate, absolute entities, but a single, interwoven, and dynamic space-time continuum. In the context of Einstein's special theory of relativity, published in 1905, time dilation is a direct consequence of the motion of an observer through space. The theory is built on two simple but revolutionary postulates that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is the same for all observers, regardless of their own motion. The second postulate is the key. If the speed of light is constant for everyone, then something else must be relative, and that something is time itself. If a spaceship is flying past you at a significant fraction of the speed of light, and it flashes a light from its floor to a mirror on its ceiling and back, you, as a stationary observer, will see the light travel on a longer, diagonal path. Since you both must agree on the speed of light, but you see the light traveling a longer distance, you must conclude that time is passing more slowly for the spaceship. This has been confirmed in numerous high-precision experiments. Highly accurate atomic clocks, when flown on fast-moving airplanes, have been shown to tick slightly slower than identical stationary clocks on the ground, the difference matching the predictions of special relativity with incredible accuracy. The particles known as muons, which are created in the upper atmosphere and travel towards the Earth at nearly the speed of light, are another powerful confirmation. They have a very short half-life and should decay long before they reach the ground. But because of time dilation, their internal clocks run slower, and a significant number of them are able to survive the journey to the Earth's surface. In the context of Einstein's general theory of relativity, published in 1915, time dilation takes on an even deeper and more profound meaning. General relativity describes gravity not as a force, but as the curvature of spacetime by mass and energy. And in this curved spacetime, the rate at which time passes is affected by the strength of the gravitational field. The stronger the gravity, the slower time flows. This gravitational time dilation means that a clock at sea level will tick slightly slower than a clock on top of a mountain, where the Earth's gravitational pull is slightly weaker. This effect, while tiny, has also been confirmed with incredible precision, most famously by the Pound-Rebka experiment in 1959, which measured the tiny gravitational redshift of photons as they traveled up a tower at Harvard University. Time dilation, in both its special and general relativistic forms, is not just a theoretical curiosity. It is a fundamental and experimentally verified feature of our universe. It challenges our intuitive, Newtonian understanding of time as a universal, absolute, and unchanging metronome. It reveals a universe that is far stranger, more dynamic, and more beautifully complex. A universe where each observer carries their own personal clock, a clock whose rhythm is shaped by the intricate and inseparable dance of space, of time, of motion, and of gravity. The theory of relativity, the groundbreaking conceptual framework that was born from the mind of Albert Einstein in the early 20th century, is the foundation upon which our entire modern understanding of space, of time, and of gravity is built. It is a story of two great theories, special relativity and general relativity. Special relativity, which Einstein introduced in his miracle year of 1905, deals with the laws of physics in the absence of gravity. It is a theory that is built on two elegantly simple but profoundly revolutionary postulates. The first is the principle of relativity, the idea that the laws of physics are the same for all observers who are in a state of uniform, constant velocity motion. The second is the principle of the constancy of the speed of light, the idea that the speed of light in a vacuum is a universal constant, the same for all observers, regardless of the motion of the light source or the observer. These two seemingly innocuous postulates, when taken together, lead to a series of stunning and deeply counterintuitive conclusions. They tell us that our familiar Newtonian concepts of absolute space and absolute time are an illusion. Instead, space and time are relative, their measurements depending on the motion of the observer. An observer in motion will experience time more slowly and will measure distances to be shorter in the direction of motion than a stationary observer. The theory also reveals a deep and intimate connection between mass and energy. As expressed in the most famous equation in all of science, E equals mc squared. But special relativity was incomplete. It did not include a description of gravity for the next 10 years. Einstein grappled with this problem, a journey that he would later describe as the most intense and intellectually demanding of his life. The result, in 1915, was his general theory of relativity, a theory of gravity that is widely regarded as one of the most beautiful and profound intellectual achievements in the history of humanity. General relativity describes gravity not as a force, as Newton had, but as a manifestation of the curvature of a unified, four-dimensional space-time continuum. In Einstein's famous words, space-time tells matter how to move, matter tells space-time how to curve. A massive object, like the Sun, warps the space-time around it, and a smaller object, like the Earth, in its orbit, is simply following the straightest possible path. A geodesic, in this curved space-time. This is a radical and beautiful reconceptualization of gravity. It is a theory that has been confirmed with stunning precision in a wide range of experiments and observations, from the subtle, anomalous precession of the orbit of Mercury to the spectacular, direct detection of the gravitational waves from colliding black holes a century later. The famous first confirmation of the theory came in 1919 when a team of astronomers, led by Arthur Eddington, observed the light from distant stars being bent as it passed by the Sun during a total solar eclipse. The amount of the bending matching Einstein's prediction perfectly. This event catapulted Einstein to global fame and cemented his status as the heir to Newton. The theory of relativity, in both its special and general forms, is more than just a scientific theory. It is a new worldview, a new way of seeing and of understanding the cosmos. It is a worldview that has replaced the static, absolute, and deterministic universe of Newton with a more dynamic, more relative, and more deeply interconnected reality. A reality where the very fabric of space and time is an active and participatory player in the grand cosmic drama. The heart of the phenomenon of time dilation, as described by special relativity, can be traced back to a single, fundamental, and experimentally verified fact. The speed of light in a vacuum is a universal constant, the same for all observers, regardless of their own relative motion. This seemingly simple statement has profound and deeply counterintuitive consequences. To understand why, let us return to the thought experiment of the light clock. Imagine a clock that consists of two parallel mirrors, with a single photon of light bouncing back and forth between them. Each round trip of the photon, each tick of the clock, corresponds to a certain, fixed interval of time. Now, imagine that this clock is on a spaceship that is moving past you at a very high speed. From the perspective of an astronaut on the spaceship, the photon is simply traveling up and down a straight, vertical path between the two mirrors. But from your perspective, as a stationary observer on the ground, the clock is moving horizontally. This means that you see the photon travel on a longer diagonal path as it moves from one mirror to the other. And here is the crucial point. According to Einstein's second postulate, you and the astronaut must both agree on the speed of the light, since you see the light travel a longer distance than the astronaut does, but you both agree on its speed. You must conclude that more time has passed for you during a single tick of the clock than has passed for the astronaut. In other words, you see the moving clock as ticking more slowly than your own. Stationary clock. This is not a trick of perception. It is a real, physical effect. The faster the spaceship moves, the longer the diagonal path the photon has to travel from your perspective. And therefore, the slower the clock will appear to tick. As the spaceship approaches the speed of light, this effect becomes more and more dramatic. From your perspective, time for the spaceship would appear to slow down to a near standstill. This has been confirmed in numerous high-precision experiments. The muons created in the upper atmosphere, traveling at close to the speed of light, have their internal clocks slowed down so much that they can survive the journey to the Earth's surface, a journey that would be impossible if their clocks were ticking at the same rate as ours. The atomic clocks on our GPS satellites, which are moving at high speeds in orbit, also experience this velocity-based time dilation, and this effect must be precisely accounted for to ensure the accuracy of the system. Time dilation is not just a feature of light clocks, it is a feature of time itself. All physical processes, the ticking of a clock, the decay of a particle, the beating of a heart, the firing of a neuron, are slowed down by the same factor when they are in a state of high-speed motion relative to an observer. It is a profound and beautiful consequence of the simple but revolutionary idea that the speed of light is the ultimate and most democratic of all cosmic constants, the same for all, regardless of their state of motion. The equation that governs the phenomenon of time dilation in special relativity is a direct mathematical consequence of the principles of relativity and the constancy of the speed of light. It is derived from the Lorentz transformations, a set of equations that describe how the measurements of space and time are related between two observers who are in a state of uniform, relative motion. The formula for time dilation is elegantly simple, yet its implications are profound. It is expressed as t equals t naught divided by the square root of 1 minus v squared over c squared. In this equation, t is the time interval measured by a stationary observer. T naught is the proper time, the time interval measured by an observer who is moving along with the clock. V is the relative velocity between the two observers, and c is the speed of light in a vacuum. The term in the denominator, the square root of 1 minus v squared over c squared, is the inverse of the Lorentz factor, often denoted by the Greek letter gamma. This factor is the key to understanding all the strange effects of special relativity. Let us break it down. If the relative velocity, v, is very small compared to the speed of light, c, as it is in all of our everyday experiences, then the ratio v squared over c squared is a tiny, almost infinitesimal number. The denominator is then the square root of a number that is very, very close to 1, which is itself very, very close to 1. This means that for everyday speeds, the time interval measured by the stationary observer, t, is, for all practical purposes, identical to the proper time. T naught, time appears to be absolute, just as Newton had assumed, but as the relative velocity, v approaches the speed of light, c, the story changes dramatically. The ratio v squared over c squared approaches 1. The term inside the square root, 1 minus v squared over c squared, approaches 0. And as the denominator approaches 0, the value of the entire expression, t, approaches infinity. This means that as an object approaches the speed of light, an observer at rest would see its time slow down, stretching out towards an infinite standstill. A clock on a spaceship traveling at 99.999% of the speed of light would appear to tick about 223 times slower than a clock on Earth. A one-year journey for the astronauts would correspond to 223 years for the people they left behind. This equation is not just a mathematical curiosity. It is a precise quantitative prediction that has been confirmed in countless experiments. The lifetimes of fast-moving, unstable particles in our particle accelerators are extended by exactly the amount predicted by this formula. The slight, but measurable, time difference between the atomic clocks on our GPS satellites and the clocks on the ground is corrected for using this very equation. It is a testament to the power of theoretical physics to uncover the deep, and often hidden, mathematical structure of our universe. a structure that can lead to predictions that are as counterintuitive as they are precisely and beautifully correct. The speed of light, approximately 300,000 kilometers per second, is not just another number in the universe. It is the ultimate cosmic speed limit. It is a fundamental and seemingly unbreakable barrier that governs the structure of spacetime and the nature of causality. According to Einstein's theory of special relativity, no object with mass can ever be accelerated to the speed of light. The reason for this lies in the deep connection between mass, energy, and velocity. As an object is accelerated, its kinetic energy increases. But according to the famous equation, E equals mc squared, energy and mass are equivalent. This means that as an object's kinetic energy increases, its relativistic mass, its resistance to further acceleration, also increases. As the object's speed approaches the speed of light, its relativistic mass approaches infinity. And to accelerate an object with infinite mass would require an infinite amount of energy, which is a physical impossibility. This cosmic speed limit is what underpins the phenomenon of time dilation. It is because the speed of light is the same for all observers that time itself must be relative. The universe, in a sense, conspires to protect this fundamental constant, and it does so by stretching and contracting the very fabric of space and time. But what about light itself? Photons, the particles of light, are massless, and so they can and must travel at the speed of light. But what does time look like from the perspective of a photon? This is a question that leads to a deep and seemingly paradoxical place. According to the time dilation formula, if you were to travel at the speed of light, the denominator of the equation would become zero, and the time dilation factor would become infinite. This means that from the perspective of an outside observer, time for the photon would appear to have stopped completely from the photon's own hypothetical perspective. The journey from a distant star to your eye would be instantaneous. The emission and the absorption of the photon would be a single, timeless event. For a photon, the entire history of the universe, from the Big Bang to the present day, happens in a single, frozen instant. This is a concept that is difficult, if not impossible, to fully wrap our minds around. And it is one that many physicists would argue is not a well-defined question, as a photon cannot have a valid rest frame, but it is a powerful and poetic illustration of the profound and beautiful way in which light is woven into the very fabric of space-time. The speed of light is not just a speed, it is the rate at which causality propagates through the universe. It is the thread that connects events, that defines the past and the future, that shapes the very geometry of our reality. And its constancy is the bedrock upon which our entire modern understanding of the cosmos is built. The comparison of time dilation effects for objects moving at different velocities reveals a smooth and continuous, but highly nonlinear, relationship between speed and the stretching of time. For the speeds we are familiar with in our everyday lives, the effects are almost immeasurably small. A person on a commercial jetliner, traveling at about 600 miles per hour, is moving at about 1/1,000,000th of the speed of light. The time dilation they experience over the course of a long 10-hour flight is on the order of a few tens of nanoseconds. It is a real physical effect, one that can be measured by our most precise atomic clocks, but it is completely imperceptible to our own human senses, even for the fastest human-made objects, like the Voyager probes, which are now traveling at over 38,000 miles per hour relative to the Sun. The time dilation effects are still relatively modest. Over their more than 40-year journey, they have aged only a few seconds less than they would have if they had remained on Earth. It is only when we begin to approach a significant fraction of the speed of light that the effects of time dilation become truly dramatic. At 50% of the speed of light, the Lorentz factor is about 1.15. This means that time for the moving object is slowed down by about 15%. A 10-year journey for the traveler would correspond to about 11.5 years for the stationary observer. At 90% of the speed of light, the Lorentz factor is about 2.29. Time is now slowed by more than a factor of 2. The 10-year journey for the traveler would correspond to almost 23 years for the stationary observer, and at 99% of the speed of light, the Lorentz factor is about 7.1. Time is slowed by a factor of over 7. At 99.99% of the speed of light, the Lorentz factor is about 71. And at 99.09999% of the speed of light, it is over 700. The relationship is exponential. Each additional 9 that we add to the velocity brings a dramatic increase in the time dilation effect. This is the tyranny of the rocket equation in its relativistic form. The energy required to accelerate to these speeds is also increasing exponentially, making each step closer to the speed of light a far greater challenge than the last. But this nonlinear relationship also has a profound, and perhaps hopeful, implication for the prospect of interstellar travel. While the distances to the stars are immense, and a journey at a conventional speed would take tens of thousands of years, a journey at a relativistic speed can, from the perspective of the traveler, be accomplished in a human lifetime. A journey to the Andromeda Galaxy, 2.5 million light-years away, would, from the perspective of an observer on Earth, take 2.5 million years, even at the speed of light. But for an astronaut on a spaceship traveling at 99.999999999% of the speed of light, the journey, due to the combined effects of time dilation and length contraction, could be accomplished in about 28 years of their own personal time. They could travel to another galaxy and back in a single lifetime. They would, of course, return to an Earth that was 5 million years older, a world that would be completely and unrecognizably transformed. But the journey itself would be possible. Time dilation, in this sense, is both a barrier and a bridge. It is a barrier that prevents us from ever reaching the speed of light. But it is also a bridge that could, in the far future, allow us to cross the vast and seemingly impassable oceans of interstellar and even intergalactic space. The twin paradox, with its story of a traveling twin who returns to find themselves younger than their earthbound sibling, is the most famous and most powerful illustration of the strange and counterintuitive nature of time in a relativistic universe. It is a story that has captivated the imagination of scientists and science fiction writers alike, and it is a story that reveals a deep and beautiful truth about the relationship between time, motion, and the very geometry of space-time. The paradox, as we have seen, is resolved by the recognition that the situation is not symmetrical. The traveling twin undergoes a period of acceleration to leave the Earth, a period of deceleration to turn around, and another period of deceleration to return. The earthbound twin remains in a single, inertial frame of reference. This asymmetry is the key. In the language of general relativity, the earthbound twin is following a straighter path through the four-dimensional space-time continuum. They are following a geodesic. The traveling twin, because of their acceleration, is following a curved path through space-time. And a fundamental principle of relativistic geometry is that the length of the path between 2 points in space-time is maximized for a geodesic. The length of a path in space-time is not a measure of distance, but of proper time. the time that is experienced by an observer moving along that path. So, the fact that the Earth-bound twin experiences more time, that they age more, is a direct consequence of the fact that they have followed a straighter, and therefore longer, path through spacetime between the two events of the twins' departure and their reunion. This is a beautiful and deeply counterintuitive result. In the familiar, Euclidean geometry of our everyday space, the shortest distance between 2 points is a straight line. But in the strange, Minkowskian geometry of spacetime, the longest time between 2 events is a straight line. Acceleration, in a sense, is a shortcut through spacetime. But the paradox also reveals something even more profound about the nature of time itself. It shows that there is no single, objective now that is shared by all observers in the universe. The concept of simultaneity is relative. 2 events that are simultaneous for one observer may not be simultaneous for another observer who is in motion relative to the first when the traveling twin is on their outbound journey. Their plane of simultaneity is tilted relative to that of the earthbound twin. They would see the earthbound twin's clock as running slower than their own. But when they turn around and begin their inbound journey, their plane of simultaneity tilts in the opposite direction. And in this process of turning around, they sweep through a vast swath of what the earthbound twin considers to be the future. This is why, when they are reunited, they find that their earthbound sibling has aged so much more. The twin paradox is a powerful reminder that our intuitive, common-sense understanding of time is a product of our own limited experience in a world of low speeds and weak gravity. The universe, at its most fundamental level, operates on a different and far stranger set of rules. It is a universe where time is not a universal metronome, but a personal and profoundly geometric journey, a journey whose duration depends on the path you take through the beautiful, dynamic, and four-dimensional landscape of space-time. The phenomenon of time dilation is not a single, monolithic effect. It is a tale of 2 different, but deeply interconnected phenomena. The first is the special relativistic or velocity-based time dilation, which arises from the relative motion of 2 observers. The second is the general relativistic or gravitational time dilation, which arises from the difference in the strength of the gravitational field experienced by 2 observers. Both of these effects are real. Both have been confirmed with incredible precision, and both are essential to a complete understanding of the nature of time in our universe. Gravitational time dilation is a direct consequence of Einstein's principle of equivalence. The idea that the effects of gravity are locally indistinguishable from the effects of acceleration. Imagine a light clock on the floor of a rocket that is accelerating upwards in deep space. An observer at the top of the rocket will see the light from the clock on the floor as being redshifted, its frequency lowered. This is because in the time it takes the light to travel from the floor to the ceiling has accelerated to a higher velocity. The observer at the top is, in a sense, running away from the light waves, which stretches them out and lowers their frequency. But by the principle of equivalence, this situation is indistinguishable from a rocket at rest in a gravitational field. Therefore, an observer at the top of a tower on Earth should see the light from a clock at the bottom as being redshifted. And since the frequency of a clock is a measure of the rate at which time is passing, this means that the observer at the top must see the clock at the bottom as ticking more slowly. Time runs slower in a stronger gravitational field. This effect is incredibly small in the Earth's weak gravitational field, but it is measurable. The famous Pound-Rebka experiment confirmed this gravitational redshift with stunning accuracy. And it is a crucial effect that must be accounted for in the GPS system. The clocks on the GPS satellites are in a weaker gravitational field than we are on the surface, and so they tick slightly faster, by about 45 microseconds per day. This gravitational effect is actually much larger than the velocity-based effect, which causes the clocks to tick about 7 microseconds per day slower. The net result is that the satellite clocks run about 38 microseconds per day faster than the clocks on the ground, a difference that, if uncorrected, would render the entire system useless in a matter of hours. The two types of time dilation are not separate, independent phenomena. They are two different aspects of the same underlying reality, the geometry of space-time. In general relativity, both the velocity of an observer and the local curvature of space-time affect the path that the observer takes through the four-dimensional space-time continuum, and the amount of proper time that an observer experiences is simply a measure of the length of that path. An observer who is moving at a high speed, or who is in a deep gravitational well, is following a shorter path through space-time, and therefore experiences less time. In the extreme environment of a black hole, these effects become truly dramatic. An observer orbiting just outside the event horizon would be subject to both extreme velocity-based time dilation, as they would have to be traveling at nearly the speed of light to maintain their orbit, and extreme gravitational time dilation. The combination of these two effects would cause their time to slow to a near standstill relative to a distant observer. The story of time dilation is a story that is written in the language of geometry. It is a story that tells us that the rhythm of our own personal clock is not a universal constant, but is a product of our own unique journey through the curved, dynamic, and beautiful four-dimensional landscape of Einstein's spacetime. The Lorentz factor. That simple but powerful mathematical expression that lies at the heart of special relativity is the key that unlocks the strange and beautiful geometry of space-time. It is a number that quantifies the degree to which our measurements of space and time are altered by relative motion. And it is a number that reveals a profound and deep connection between these two, seemingly separate, aspects of our reality. The formula for the Lorentz factor, gamma, is 1 divided by the square root of 1 minus v squared over c squared. It is a number that is always greater than or equal to 1. At rest, gamma is exactly 1. There are no relativistic effects. As the velocity, v, increases, gamma also increases, slowly at first, and then more and more rapidly as v approaches the speed of light. C. As v approaches c, gamma approaches infinity. This single, velocity-dependent factor governs all the strange phenomena of special relativity. The time measured by a stationary observer is the proper time measured by a moving observer multiplied by the Lorentz factor. The length of a moving object, as measured by a stationary observer, is its proper length divided by the Lorentz factor. And the relativistic mass of a moving object is its rest mass multiplied by the Lorentz factor. The Lorentz factor is not just a mathematical curiosity. It is a direct expression of the underlying geometrical structure of space-time. In the three-dimensional, Euclidean space of our everyday experience, the distance between 2 points is given by the Pythagorean theorem. The square of the distance is the sum of the squares of the differences in the x, y, and z coordinates. This distance is an invariant. It is the same for all observers, regardless of their orientation. In the four-dimensional space-time of special relativity, there is a similar, but slightly different, invariant quantity, the space-time interval. The square of the space-time interval between two events is given by the square of the difference in their time coordinates minus the sum of the squares of the differences in their spatial coordinates. This is a kind of hyperbolic or Minkowskian geometry. The Lorentz transformations are precisely the set of transformations that leave this space-time interval invariant. They are the rotations in this four-dimensional space-time. And the Lorentz factor is a direct consequence of this strange geometry. just as a rotation in normal space mixes the x and y coordinates. A Lorentz boost, a change in velocity, mixes the space and time coordinates. My time is a mixture of your time and your space. My space is a mixture of your space and your time. The Lorentz factor is the mathematical term that governs this mixing. This has profound implications. It means that space and time are not independent. They are two aspects of a single, unified reality. The amount of space and time that you measure between two events depends on your own state of motion. What I see as a pure time interval, you might see as a combination of a time interval and a space interval. The only thing we can all agree on is the space-time interval. The Lorentz factor, then, is more than just a formula. It is a window into the deep, and often counterintuitive, structure of our reality. It is a mathematical expression of the profound and beautiful idea that we are all travelers through a single, unified, four-dimensional space-time, and that the individual paths we take through this landscape are what define our own, personal, and profoundly relative experiences of space and of time. The concept of an inertial frame of reference is a cornerstone of physics, a foundational idea that is essential for understanding the laws of motion and the principles of relativity. An inertial frame is, in essence, a perspective, a coordinate system, from which an observer who is not subject to any external forces would be seen to be at rest or moving at a constant velocity. It is a frame of reference that is not accelerating. The principle of relativity, in both its Galilean and its Einsteinian forms, is a statement about the laws of physics as seen from these inertial frames. It states that the fundamental laws of nature are the same in all inertial frames. There is no special, absolute, or privileged state of rest. The laws of physics are democratic. This has profound consequences. It means that you can never, even in principle, perform an experiment in a closed, windowless room to determine whether you are at rest or moving at a constant velocity. The ball you throw will follow the same parabolic arc. The pendulum will swing with the same period. The laws of electricity and magnetism will be the same. This is the world of special relativity. But what happens when we are in a non-inertial frame? A frame that is accelerating? This is the world of general relativity. Einstein's great insight was to recognize that the effects of acceleration are locally indistinguishable from the effects of gravity. An observer in a rocket that is accelerating in deep space will feel a force that is identical to the force of gravity. This principle of equivalence is the conceptual heart of general relativity, and it is what allowed Einstein to generalize the principle of relativity to include the effects of gravity and acceleration. In this more general picture, the distinction between inertial and non-inertial frames becomes a bit more subtle. In a curved spacetime, there are no truly global inertial frames, but we can always define a local inertial frame, a small region of spacetime over which the effects of gravity are negligible, and where the laws of special relativity hold. This is the frame of a freely falling observer. An astronaut in orbit around the Earth is in a state of free fall. From their perspective, they are weightless, and they are in a local inertial frame. The concept of inertial frames is also what allows us to make sense of the twin paradox. The Earth-bound twin remains in a single, inertial frame for the entire journey. The traveling twin, on the other hand, must accelerate to leave, to turn around, and to return. They are occupying a series of different, non-inertial frames. It is this difference in their paths through space-time, this difference in the frames of reference they occupy, that is the source of the asymmetry and the reason for their different experience stages. The concept of a frame of reference is a powerful and essential tool in physics. It is the lens through which we view the universe, the coordinate system upon which we map its laws. And the great revolutions of modern physics have been, in a very real sense, revolutions in our understanding of these frames, a journey from the absolute, privileged frame of Aristotle to the democratic, inertial frames of Galileo and Newton, and finally to the dynamic, local, and geometrically profound frames of Einstein's relativity. The experimental evidence for time dilation is not subtle or ambiguous. It is a robust, well-established, and repeatedly verified feature of our universe. One of the earliest and most beautiful confirmations came from the study of cosmic ray muons. Muons are unstable, subatomic particles that are created in the upper atmosphere when high-energy cosmic rays from deep space collide with the nuclei of air molecules. These muons are created at a high altitude, about 10 to 15 kilometers above the Earth's surface, and they travel towards us at very close to the speed of light. At rest, a muon has a very short half-life of about 2.2 microseconds. This means that even traveling at the speed of light, a typical muon should only be able to travel about 660 meters before it decays. The vast majority of them should decay long before they ever reach the ground. And yet, when we place detectors on the surface of the Earth, we detect a significant flux of these cosmic ray muons. The reason they can survive the journey is time dilation. From our perspective, as observers on the ground, the muon's internal clock is running slow. Its lifetime is stretched or dilated by the Lorentz factor, which, for a muon traveling at 99.5% of the speed of light, is about 10. This means that its effective lifetime, in our frame of reference, is not 2.2 microseconds, but about 22 microseconds. This is more than enough time for it to travel the full distance from the upper atmosphere to the ground. The observation of these atmospheric muons is a direct and beautiful confirmation of the predictions of special relativity. Another, and even more precise, line of evidence comes from the use of atomic clocks. An atomic clock is an incredibly precise timekeeping device that uses the regular and universal oscillations of atoms as its pendulum. In the famous Haffel-Keating experiment of 1971, 4 cesium beam atomic clocks were flown around the world on commercial airliners, once eastbound and once westbound. When their times were compared with a reference clock that had remained on the ground at the U.S. Naval Observatory, a tiny but statistically significant discrepancy was found. The clocks that had flown had aged slightly less than the clock on the ground, and the amount of the discrepancy was in perfect agreement with the combined predictions of both special relativistic and general relativistic time dilation. This experiment, and many other more precise versions of it that have been performed since, provides a direct and irrefutable confirmation of the reality of relativistic time. And as we have seen, the entire multi-billion-dollar global positioning system is a continuously operating global-scale experiment that is constantly confirming the reality of time dilation. The atomic clocks on the GPS satellites must be constantly corrected for the fact that they are ticking at a different rate than the clocks on the ground. Without these relativistic corrections, the system would fail within minutes. The evidence for time dilation is not just a curiosity for physicists. It is a fundamental feature of our reality, a feature that has been woven into the very fabric of our modern technological world. It is a testament to the power of Einstein's profound and often counterintuitive insights into the deep and beautifully geometric nature of space and of time. The implications of time dilation for future, long-duration human space missions, particularly for the prospect of interstellar travel, are both profound and deeply paradoxical. On the one hand, time dilation is the great enabler. The distances to the stars are so vast that a journey at any sublight speed that we can currently imagine would take tens of thousands or even millions of years. But for a crew on a spaceship traveling at a significant fraction of the speed of light, the journey can be accomplished in a human lifetime. The traveler's own personal biological clock is slowed down relative to the rest of the universe, allowing them to traverse the immense gulfs of interstellar space in a subjectively reasonable amount of time. This is the great hope of relativistic spaceflight. But this hope comes with a profound, and perhaps tragic, price: a complete and irreversible disconnection from the temporal stream of their home world. The astronauts who embark on such a journey would be, in a very real sense, time travelers into the future of the human race. They would return from their journey to a world that they would not recognize, a world where centuries or even millennia have passed. Their friends, their families, their entire culture would be a distant historical memory. This raises a host of deep, and as yet unanswered, psychological and societal questions. What would be the psychological impact on a human being of such a profound and permanent form of temporal exile? How could a society deal with the return of these ghosts from a long-lost past? The story of interstellar travel is not just a story of technological challenges. It is also a story of a deep and potentially tragic human drama, and the physical effects of such a journey would also be immense. Traveling at close to the speed of light, even the thinnest wisps of interstellar gas would become a stream of high-energy particles, requiring a powerful and robust form of radiation shielding to protect the crew. The engineering challenges of building a starship that could accelerate to and decelerate from such incredible speeds are far beyond our current capabilities. But the very existence of time dilation, the very fact that the laws of physics allow for this stretching of time, provides a glimmer of a hope, a theoretical pathway that could one day allow our descendants to break the chains of our own small solar system and to become a truly galactic species. It is a dream that is fraught with paradox, with difficulty, and with a profound sense of human sacrifice, but it is also a dream that is deeply and powerfully woven into the very fabric of our exploratory and endlessly curious human spirit. The synchronization of clocks, a seemingly simple and mundane task in our everyday lives, becomes a profound and complex challenge in a relativistic universe. The very concept of simultaneity, the idea that two events can happen at the same time, is not an absolute but a relative one. According to special relativity, two events that are simultaneous in one inertial frame of reference will not, in general, be simultaneous in another frame that is in motion relative to the first. This relativity of simultaneity is a direct consequence of the constancy of the speed of light, and it is at the very heart of the strange, geometric nature of spacetime. Imagine a long train moving at a high speed. An observer is standing in the exact middle of one of the train cars. Two lightning bolts strike the front and the back of the train car simultaneously, from the perspective of an observer standing on the ground next to the tracks. Since the ground observer is in the middle of the two strike points, the light from the two flashes will reach them at the same time, and they will correctly conclude that the strikes were simultaneous. But what about the observer on the train? From their perspective, they are moving towards the light flash from the front of the car and away from the light flash from the back. This means that the light from the front strike will reach them before the light from the back strike. Since they know they are in the middle of the car, they will be forced to conclude that the lightning must have struck the front of the car before it struck the back. The two events were not simultaneous in their frame of reference. This is not a matter of perception or illusion. It is a real physical effect. There is no single, universal now that is shared by all observers in the universe. Each observer has their own personal slice of space-time that they consider to be the present, and the orientation of this slice depends on their state of motion. This has profound implications for our understanding of causality and the structure of time. It is what underpins the block universe picture, the idea that the past, present, and future all exist in a single, timeless, four-dimensional reality. And it has very real and very practical, Consequences for any technology that relies on the precise synchronization of distant clocks. Like the GPS system. The GPS system works by trilateration. A receiver on the ground measures the time it takes for signals to arrive from at least 4 different satellites. Since the signals travel at the speed of light, this time-of-flight measurement gives the distance to each satellite. By knowing the precise position of the satellites and their distances, the receiver can calculate its own three-dimensional position. But this entire system depends on all the clocks on the satellites and the clock in the receiver being perfectly synchronized, and in a relativistic universe. This is a non-trivial task. The clocks on the satellites are subject to both special and general relativistic effects, which cause them to tick at a different rate than the clocks on the ground. These effects must be precisely calculated and corrected for. The system must also account for the relativity of simultaneity. The very definition of a common time for the entire global system is a complex and carefully constructed convention. The synchronization of clocks in a relativistic world is a beautiful and powerful example of how the deep and often counterintuitive principles of fundamental physics are not just abstract, theoretical ideas, but are woven into the very fabric of our modern technological civilization. The relationship between time and velocity in a relativistic universe is a deep and beautiful one, a story that is told in the elegant mathematical language of the Lorentz transformations and the Minkowskian geometry of spacetime. It is a story that has replaced the simple, linear, and absolute time of Newton with a more dynamic, more personal, and more profoundly interconnected reality. The faster you move through space, the slower you move through time. This is not just a catchy phrase. It is a precise, quantitative statement about the structure of our universe. Every object in the universe can be thought of as having a 4-velocity through the 4-dimensional space-time continuum. The length of this 4-velocity vector is always, and for all observers, equal to the speed of light. This is a strange and beautiful idea. It means that everything in the universe is always traveling at the speed of light through space-time. When you are at rest in space, all of your motion is through the time dimension. You are aging, you are moving into the future at the maximum possible rate. But as you begin to move through space, a portion of your motion through time is rotated into motion through space. You are, in a sense, trading a bit of your speed through time for speed through space, in a way that keeps your total 4-dimensional speed constant at the speed of light. This is why your clock, your personal rate of passage through time, slows down from the perspective of a stationary observer. This is the deep geometric meaning of time dilation. It is a consequence of the simple but profound fact that we are all, always, surfing the cosmic speed limit, the speed of light, through the unified 4-dimensional ocean of space-time. This has profound implications for our understanding of causality. The speed of light is not just a speed, it is the boundary of the light cone, the region of space-time that can be causally connected to a given event. The past light cone is the set of all events that could have influenced the present event. The future light cone is the set of all events that the present event can influence. Events that lie outside of this light cone are in a region of space-time called elsewhere. They are so far away in space and so close in time that not even a signal traveling at the speed of light could connect them. They are, in a very real sense, causally disconnected. The structure of the light cone, the fact that there is a finite and universal speed of causality, is what gives space-time its definite causal structure. It is what ensures that cause always precedes effect in all frames of reference. It is what prevents the paradoxes of backward-in-time travel. The relationship between time and velocity is one of the most beautiful and profound discoveries in the history of science. It is a discovery that has taken us from a simple, intuitive, and ultimately wrong picture of the world to a deeper, more subtle, and more beautifully interconnected understanding of the fundamental fabric of our reality. The role of acceleration in the phenomenon of time dilation is a subtle and often misunderstood aspect of relativity. In the standard pedagogical explanation of the twin paradox, it is often said that the acceleration of the traveling twin is the cause of the time difference, but this is not quite correct. Time dilation, in its special relativistic form, is a function of velocity, not acceleration. It is the long period of high-speed, constant velocity travel that is primarily responsible for the accumulated time difference. So, what is the role of acceleration? The acceleration is what allows the traveling twin to change their inertial frame of reference. It is what allows them to leave the Earth, to turn around, and to come back. Without acceleration, there can be no round trip, and therefore, no paradox. The acceleration is the agent of the asymmetry in the twins' paths through space-time. It is what makes the traveling twins' world line a curved path, while the earthbound twins' world line is a straight one in the context of general relativity. However, acceleration takes on a much deeper and more fundamental meaning. The principle of equivalence tells us that the effects of acceleration are locally indistinguishable from the effects of gravity. This means that acceleration itself can be a source of time dilation. An observer in an accelerating rocket will see a clock at the back of the rocket as ticking slower than a clock at the front. This is directly analogous to the gravitational time dilation, where a clock in a stronger gravitational field ticks slower than a clock in a weaker field. This acceleration-based time dilation is a real physical effect, and it does contribute to the overall time difference in the twin paradox, particularly during the brief, but intense, periods of acceleration and deceleration at the beginning, middle, and end of the journey. But for a long interstellar journey, where the periods of acceleration are short compared to the long period of high-speed cruising, the velocity-based time dilation is the dominant effect. The relationship between acceleration, gravity, and time is one of the most profound and beautiful aspects of Einstein's theory. It tells us that the very structure of spacetime is dynamic and responsive, its geometry shaped by the presence of matter and energy, and its temporal rhythm influenced by the motion and the acceleration of the observers who travel through it. The concept of time dilation, with its strange and beautiful implications for the relativity of time, is not just a curiosity for physicists and science fiction writers. It is a profound and powerful mirror for our own subjective and often fluid experience of time. In our everyday lives, we are all time travelers. We all know the experience of time stretching and contracting, of a single, terrifying second of a car crash expanding into an eternity, of a joyful, sun-drenched afternoon with a loved one dissolving in the blink of an eye. Our emotional and psychological state has a powerful and deeply real effect on our perception of duration. This is not the same as the physical time dilation of relativity, but it is a powerful, experiential parallel. It tells us that our experience of time is not just a passive reading of an external, objective clock. It is an active, creative, and deeply personal process, a process that is shaped by the quality of our attention, the intensity of our emotions, and the meaning we give to our experiences. The philosophical implications of this are immense. If time is not an absolute, universal constant, but is a personal and relative experience, then what does this say about the nature of reality itself? Does it suggest a universe that is more subjective, more participatory, more mind-like than our classical materialistic worldview would allow? The great questions that arise from time dilation, the nature of simultaneity, the structure of causality, the relationship between the past, the present, and the future are not just questions of physics. They are questions of metaphysics. They are questions that push us to the very limits of our language and our conceptual frameworks. They invite us to adopt a stance of greater humility and greater wonder in the face of a universe that is far stranger and far more mysterious than we can ever fully comprehend. The beauty of a concept like time dilation is that it is both a precise, mathematical, and experimentally verified scientific theory, and also a deep poetic and endlessly generative source of philosophical and existential reflection. It is a concept that bridges the two cultures of science and the humanities. It is a concept that speaks to both our rational, analytical minds and our intuitive, wondering hearts. And in doing so, it enriches our understanding not just of the universe, but of ourselves, and of our own strange, beautiful, and profoundly relative journey through the mysterious landscape of time. The measurement of the subtle, and often minuscule, effects of time dilation requires some of the most precise and sophisticated instruments ever created by human beings. It is a field of experimental physics where the quest for accuracy is a constant and often heroic battle against the noise and the imperfections of the real world. The workhorse of this field is the atomic clock. A modern cesium fountain atomic clock is a device of almost unimaginable precision. It is a clock that would not gain or lose a single second in over 300 million years. It is this incredible stability that allows us to detect the tiny, relativistic effects of time dilation in our own terrestrial environment. By comparing the time kept by two of these clocks, one at sea level and one on top of a mountain, we can measure the tiny but real effect of gravitational time dilation. By flying one of these clocks in an airplane, we can measure the combined effects of both velocity-based and gravity-based time dilation. These are experiments of exquisite subtlety and precision, and their consistent agreement with the predictions of Einstein's theory is one of the most powerful and beautiful confirmations of our modern understanding of space and time. But to test time dilation in more extreme regimes, we must turn to the cosmos itself. The universe is a natural laboratory, a place where nature has provided us with clocks that are moving at incredible speeds and in incredibly strong gravitational fields. Pulsars, for example, are rapidly spinning neutron stars that emit beams of radio waves that sweep across the cosmos like a lighthouse beam. From our perspective on Earth, we see these beams as incredibly regular pulses of radio emission. They are some of the most stable and precise clocks in the entire universe. And by carefully timing the arrival of these pulses, we can use pulsars as powerful probes of relativistic effects. In 1974, the astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, a system of two neutron stars orbiting each other. By timing the pulses from one of these stars over a period of many years, they were able to show that the orbit of the two stars was slowly decaying, that they were spiraling in towards each other. This orbital decay was caused by the emission of gravitational waves, the faint ripples in spacetime that were predicted by Einstein's theory. And the rate of this decay was imperfect and stunning. Agreement with the predictions of general relativity. This discovery, which earned Hulse and Taylor the Nobel Prize in Physics, was the first indirect but overwhelmingly powerful confirmation of the existence of gravitational waves, and it was also a precise test of the theory of general relativity in the strong field regime. This system also provides a beautiful and extreme test of time dilation. As the pulsar moves in its elliptical orbit, its speed and its distance from its companion star are constantly changing. This means that it is subject to both special and general relativistic time dilation effects, which cause its pulse period to vary in a subtle but predictable way over the course of its orbit. The measurement of these tiny relativistic effects in the timing of the binary pulsar is one of the most precise and beautiful tests of Einstein's theory ever performed. It is a testament to the power of human ingenuity to use the faint, rhythmic whispers from a long-dead star, thousands of light years away, to confirm some of the deepest and most profound truths about the fundamental nature of our universe. The prospect of human space travel to distant planets, and one day, perhaps, to the stars, is a dream that is deeply and powerfully woven into the fabric of our culture, but it is a dream that must confront the strange and often counterintuitive realities of a relativistic universe. And one of the most profound of these is time dilation. For a mission to a nearby planet, like Mars, the effects of time dilation will be relatively small. The journey will take about 6 to 9 months at the speeds we can currently achieve. And the accumulated time difference between the crew and the people on Earth will be on the order of a few minutes. This is a scientifically interesting, but not a humanly significant, effect. But as we begin to contemplate more ambitious, long-duration missions, like the establishment of a permanent, self-sustaining colony on Mars, the cumulative effects of time dilation, even these small ones, will begin to matter. A Martian colonist living their entire life in a slightly weaker gravitational field than the Earth's will age at a slightly different rate than their terrestrial counterparts. Over a lifetime, this could amount to a difference of a few seconds. This is not a large effect, but it is a real one, and it is a subtle but constant reminder that the colonists are living in a different and physically distinct world. It is when we begin to dream of interstellar travel that time dilation becomes the central and most paradoxical character in the human drama of exploration. A journey to even the nearest star, Proxima Centauri, 4.2 light-years away, would, at a speed of 10% of the speed of light, take about 42 years. The crew would age 42 years, but due to time dilation, a slightly longer period of time, about 42.2 years, would have passed on Earth. This is a small but noticeable difference. But if we could achieve a speed of 99% of the speed of light, the journey would, from the perspective of the crew, take about 4.2 years. But upon their return, they would find that over 59 years had passed on Earth. They would have traveled into the future. This is the profound and deeply human paradox of interstellar travel. It is a journey that offers the promise of new worlds, of new discoveries, of a new future for humanity. But it is also a journey that demands a profound and perhaps unbearable sacrifice, the sacrifice of one's own personal connection to the temporal stream of human history. The interstellar traveler is an exile in time, a person who has stepped off the river of their own culture and who can never truly return. The societal and psychological implications of this are immense. How would we choose the people for such a mission? What kind of society would they create on their new world? A society that is, by its very nature, out of sync with its home world. And what would it mean for humanity to become a species that is spread not just across space, but also across time? These are not just questions for science fiction writers. They are deep and very real. Questions that we will have to confront if we are ever to become a truly spacefaring civilization. The journey to the stars is not just a journey of technology. It is also a journey into the deepest and most challenging frontiers of the human heart. The challenges of communication across the vast, relativistic distances of space are as profound as the challenges of travel itself. In our modern terrestrial world, we have become accustomed to the illusion of instantaneous communication. But in the cosmos, we are always and forever bound by the finite speed of light. And in a universe where time itself is relative, the very concept of a simple, back-and-forth conversation becomes a complex and often paradoxical affair. For a mission to Mars, the one-way light travel time can be up to 24 minutes. This means that a conversation between an astronaut on Mars and mission control on Earth would have a round-trip delay of almost an hour. This makes real-time, interactive communication impossible. It is a conversation that is more like an exchange of letters than a phone call. This is why a high degree of autonomy for the crew and for the robotic systems is so essential. But for a mission that is traveling at a significant fraction of the speed of light, the situation becomes even stranger and more complex. The effects of time dilation and the relativity of simultaneity would turn any attempt at communication into a mind-bending puzzle. Let us return to our twin paradox. When the traveling twin is on their outbound journey, they will see the earthbound twin's clock as running slow. Any message they receive from Earth will be, from their perspective, time-stamped with an earlier time than they would expect. And any message they send back to Earth will, from the perspective of the earthbound twin, arrive at a later time and with a greater interval between messages than when they were sent. The communication would be stretched or time-dilated. The situation is further complicated by the Doppler effect. The radio waves that are used for communication would be significantly redshifted as the spacecraft moves away from the Earth, and blue-shifted as it moves towards it. This would require a sophisticated and adaptive communication system that can constantly adjust its frequency to compensate for this effect. And the relativity of simultaneity would make the very concept of a synchronized communication a complex and frame-dependent convention. The challenges are immense, but they are not, in principle, insurmountable. We can design communication protocols that are robust to these relativistic effects. We can use powerful error-correcting codes to ensure the integrity of the messages, and we can develop new, more philosophical and more patient modes of communication, modes that are adapted to the vast temporal and spatial scales of interstellar space. The dream of a future, galactic civilization, a network of human colonies spread across the stars, is a dream of a civilization that has learned to live with and to communicate across these profound relativistic distances. It would be a civilization where a conversation might take a century, where a pen pal might live on a world whose present is our distant future. It is a vision of a human community that is not just spread across space, but is also a rich and complex tapestry woven across time. It is a vision that challenges our deepest and most cherished notions of community, of connection, and of what it means to be a part of a single human story. The prospect of human travel to distant star systems, the ultimate dream of space exploration, is a concept that forces us to confront the most extreme and most profound implications of time dilation. It is a journey that would not just be a passage through space, but a passage into the deep future of our own species. While the technological challenges of building a starship that can travel at a significant fraction of the speed of light are far beyond our current capabilities. The physics of such a journey is well understood, and that physics tells us a story that is both inspiring and deeply melancholic. It is inspiring because it tells us that the vast and seemingly impassable distances between the stars are not an absolute barrier. An astronaut on a spaceship traveling at close to the speed of light could, from their own personal perspective, make the journey to a nearby star and back in a matter of years or decades. Time dilation would be their shield, their vessel, the magic that allows them to traverse the cosmic ocean in a human lifetime. But it is a journey that is also melancholic because it is a journey of ultimate and irreversible farewell. The interstellar traveler is an exile in time. They would return to a home that is no longer their home, to a world where everyone and everything they have ever known has passed into the mists of history. This is a theme that has been explored with profound beauty and sadness in much of science fiction, from the stories of Poul Anderson to the film Interstellar. It is a story that speaks to our deepest fears of loss, of loneliness, of the relentless and unforgiving passage of time, and it raises a host of deep and as yet unanswered ethical and societal questions. What kind of person would be willing to make such a sacrifice? What would be the psychological impact of such a profound and permanent disconnection from the human story? And what would be the impact on the society that is left behind? A society that would have to live with the knowledge that their friends, their family members, their heroes, have journeyed into a future that they themselves will never see. But the story of interstellar travel is not just a story of human beings. It is also a story of the very nature of life and of intelligence in the cosmos. The immense timescales of stellar and galactic evolution mean that if there are other intelligent civilizations in our galaxy, they are likely to be, from our perspective, either incredibly ancient or not yet born. The chance of two independent, technological civilizations existing at the same time, and in the same local region of the galaxy, is incredibly small. This is one of the possible resolutions to the Fermi paradox. The galaxy may be teeming with life, but it may also be full of the ruins of long-dead civilizations and the seeds of civilizations that have not yet arisen. The story of life in the cosmos may be a story that is not played out in space, but in time, and time dilation. With its ability to bridge these vast temporal gulfs, could, in the far future, be the key that allows our descendants to become the archaeologists of the galaxy, to visit the ruins of ancient alien worlds, and to perhaps, one day, be the ancient aliens for a new young civilization that is just beginning to look up at the stars and to wonder. The concept of simultaneity, the seemingly simple idea that two events can happen at the same time, is one of the first and most profound casualties of Einstein's theory of relativity. In our everyday Newtonian world, time is absolute. There is a single, universal now that is shared by all observers, everywhere in the universe. But in a relativistic universe, where the speed of light is the only absolute, simultaneity itself becomes a relative and frame-dependent concept. The classic thought experiment to illustrate this involves a long train, a flash of light, and two observers. Imagine a flash of light is emitted from the exact center of a moving train car. For an observer on the train, the light will travel an equal distance to the front and the back of the car, and so they will see the light flashes arrive at the two ends simultaneously. But for an observer standing on the ground, watching the train go by, the situation is different. They see the back of the train car moving towards the point where the light was emitted, and the front of the car moving away from it. This means that the light has a shorter distance to travel to reach the back of the car, and a longer distance to travel to reach the front. Since the speed of light is the same for both observers, the ground observer will see the light flash hit the back of the car before it hits the front. The two events, which were simultaneous for the observer on the train, are not simultaneous for the observer on the ground. This is not a matter of illusion or perception. It is a real physical effect, a direct consequence of the fundamental geometry of space-time. This has profound implications. It means that there is no objective, universal present moment. Your now is not my now. Each observer has their own unique slice of space-time that they consider to be the present, and the orientation of this slice depends on their state of motion. This is the foundation of the block universe interpretation of space-time, the idea that the past, the present, and the future all exist in a single, timeless, four-dimensional reality. The flow of time is an illusion, a trick of our consciousness as it moves along its world line through this static, pre-existing block. This also has a deep connection to the nature of causality. While the order of two events can be relative, this is only true for events that are space-like, separated events that are so far apart in space that not even a signal traveling at the speed of light could connect them, for events that are time-like separated, events that lie within each other's past or future, light cones. The causal order is absolute. All observers will agree that the cause precedes the effect. The structure of spacetime, with its universal speed limit, protects the fundamental, logical structure of causality. The relativity of simultaneity is one of the most difficult and most deeply unsettling concepts in all of modern physics. It challenged our most basic and most cherished intuitions about the nature of time. But it is also a beautiful and profound idea. It is a window into a reality that is far stranger, more interconnected, and more beautifully geometric than our classical, common-sense minds could ever have imagined, and it is a concept that has very real and very practical consequences, underpinning the entire global system of synchronization that allows for technologies like the GPS to function with such incredible precision. The relationship between energy and time dilation is one of the most fundamental and profound aspects of Einstein's theory of relativity. It is a relationship that is encapsulated in the two great pillars of his work, the equivalence of mass and energy from special relativity, and the equivalence of gravity and acceleration from general relativity. In special relativity, as we have seen, the energy of a moving object increases with its velocity. This is not just its kinetic energy, it is a real increase in its relativistic mass, its inertia, its resistance to further acceleration. The famous equation, E equals mc squared, tells us that mass is a form of concentrated, stored energy. But the full relativistic version of this equation tells us that the total energy of a moving object is its rest mass energy plus its kinetic energy. And as an object's velocity approaches the speed of light, its total energy, and therefore its relativistic mass, approaches infinity. This is why it is impossible for an object with mass to ever reach the speed of light. The energy required would be infinite. This increase in energy is directly and intimately linked to the phenomenon of time dilation. The Lorentz factor, which governs the increase in energy, is the same factor that governs the slowing of time. They are two sides of the same relativistic coin. In general relativity, the connection becomes even deeper. The theory tells us that all forms of energy, not just mass, are a source of gravity. The energy of a compressed spring, the thermal energy of a hot gas, the energy of the electromagnetic field, all of these contribute to the curvature of space-time. This is the principle of the stress-energy tensor, the mathematical object that is the source of gravity in Einstein's field equations. And since all energy is a source of gravity, and since gravity affects the flow of time, then all energy must, in a sense, be a source of time dilation. A region of space with a high energy density, whether it is from matter, from radiation, or from the zero-point energy of the vacuum itself, will be a region where time flows more slowly. This is the deep, underlying connection between energy and time in our universe. They are not separate, independent entities. They are two aspects of a single, unified, and dynamic reality. A reality that is described by the beautiful and profoundly geometric language of Einstein's spacetime. In the extreme environments of the cosmos, like the core of a neutron star or the accretion disk around a black hole, where the energy densities are almost unimaginably high, these effects become truly dramatic. It is in these cosmic laboratories that we can see the full and awesome power of the relationship between energy, gravity, and the very rhythm of time itself. The phenomenon of time dilation around a black hole is one of the most extreme and most mind-bending predictions of Einstein's general theory of relativity. A black hole is a region of spacetime where gravity is so strong that the curvature of spacetime becomes infinite at its center, a point known as the singularity. The boundary of the black hole is its event horizon, a one-way membrane from which nothing, not even light, can escape. And as one approaches this event horizon, the effects of gravitational time dilation become infinitely large. For an observer who is hovering at a fixed distance just outside the event horizon, time would be slowed to a near standstill relative to a distant, stationary observer. A single second for the hovering observer could correspond to 1 billion years for the rest of the universe. This is not just a theoretical curiosity. It has real, observable consequences. An object that is falling into a black hole will, from the perspective of a distant observer, appear to slow down as it approaches the event horizon. Its light will become more and more redshifted, its image fainter and fainter, until it seems to be frozen, hovering at the edge of the black hole for all of eternity. From the perspective of the falling object itself, however, nothing unusual happens as it crosses the event horizon. It passes through the boundary in a finite amount of its own, proper time. But once inside, its fate is sealed. All possible paths, all possible world lines within the event horizon lead inevitably to the central singularity. The future, for any object that has crossed the event horizon, is not a direction in time, but a location in space. This extreme time dilation has profound implications for our understanding of the nature of time itself. It shows that time is not a universal, immutable background, but a local, dynamic, and profoundly pliable entity, a thing that can be stretched, and in the extreme case of a black hole, effectively stopped by the power of gravity. It also raises a host of deep, and as yet unanswered, questions at the intersection of general relativity and quantum mechanics. What happens to time at the singularity itself, where the curvature of space-time is infinite and our current theories break down? And what is the ultimate fate of the information that falls into a black hole? The study of time dilation in the extreme environment of a black hole is a journey to the very edge of our current understanding. A journey into a realm where the familiar concepts of space, of time, and of reality itself begin to lose their meaning. It is a journey that is not just about physics, but about the very limits of human thought. The role of the observer in the phenomenon of time dilation is a subtle, but crucial one. In the context of relativity, an observer is not necessarily a conscious human being. It is simply a frame of reference, a coordinate system from which measurements of space and time are made, and the central and revolutionary insight of Einstein's theory is that these measurements are not absolute, but are relative to the state of motion and the gravitational environment of the observer. The time that you measure, the length that you measure, the simultaneity that you perceive, all of these depend on your own personal frame of reference. This is a profound departure from the classical Newtonian worldview, where space and time were a fixed, absolute, and universal stage upon which the drama of the cosmos unfolded. In the relativistic worldview, each observer is the center of their own personal universe of measurements, and the laws of physics, the Lorentz transformations, provide the precise mathematical rules for translating the measurements made in one frame of reference into the measurements made in another. This does not mean that reality is purely subjective. There are certain quantities, like the speed of light in a vacuum and the space-time interval, that are invariant, the same for all observers. These invariants are the objective bedrock upon which the relative and frame-dependent measurements of space and time are built. The universe is not a chaotic, solipsistic free-for-all. It is a deeply structured and beautifully ordered reality. A reality where the subjective perspectives of all possible observers are woven together into a single, coherent, and mathematically consistent whole. The role of the observer in relativity, then, is not to create reality, as is sometimes suggested in some of the more mystical interpretations of quantum mechanics. It is, rather, to provide a specific and necessarily partial perspective on a single, underlying, and four-dimensional reality. Imagine a large, complex sculpture. Different observers, standing in different positions around the sculpture, will see different two-dimensional projections of it. One will see its front, another its side, another its top. Each of these perspectives is a valid, but incomplete, representation of the whole, three-dimensional object. In the same way, each observer in spacetime is experiencing a different three-dimensional slice or projection of the four-dimensional block universe. My now is a different slice than your now. My space is a different slice than your space. The role of the observer is to define the slice. And the theory of relativity is the set of rules that tells us how all these different possible slices are related to each other, how they are all part of the same, single, and beautifully unified four-dimensional sculpture. The concept of a frame of reference is one of the most fundamental and powerful ideas in all of physics. It is, in its essence, a perspective, a point of view, a coordinate system from which we can describe the motion and the interaction of objects in the universe. And the history of physics, in many ways, can be seen as a history of a deepening and often revolutionary understanding of the nature of these frames of reference. In the Aristotelian worldview, there was a single, absolute, and privileged frame of reference, the frame of the stationary, unmoving Earth at the center of the universe. All motion was to be understood relative to this absolute standard of rest. The Great Copernican Revolution was a revolution in our understanding of these frames. It was the recognition that the Earth is not at rest, that it is just another planet in motion around the Sun. This led to the Galilean principle of relativity, which states that the laws of mechanics are the same in all inertial frames of reference frames that are in a state of uniform, constant velocity motion. There is no absolute state of rest. This is the foundation of classical Newtonian physics. But even in the Newtonian universe, time was still considered to be absolute. All observers, regardless of their state of motion, were thought to share a single universal clock. Einstein's special theory of relativity was a second and even more profound revolution. It extended the principle of relativity to include not just mechanics, but all the laws of physics, including the laws of electromagnetism. And in doing so, it was forced to abandon the idea of absolute time. In the Einsteinian universe, each inertial frame has its own personal time, its own personal definition of simultaneity. The only absolute is the speed of light. But the world is not just made of objects in uniform motion. It is also a world of acceleration, of forces, of gravity. And this is where Einstein's general theory of relativity comes in. It is a theory that extends the principle of relativity to include non-inertial, accelerating frames of reference, and it does so through the profound and beautiful insight of the principle of equivalence, the idea that the effects of gravity are locally indistinguishable from the effects of acceleration. This leads to a new and deeply geometric understanding of gravity. In a curved space-time, there are no truly global inertial frames, but we can always define a local inertial frame, a small, freely falling region of space-time where the effects of gravity are canceled out, and where the laws of special relativity hold true. An astronaut floating weightlessly in a spacecraft that is in orbit around the Earth is, from this perspective, in a local inertial frame. They are following a geodesic, the straightest possible path, in the curved space-time around the Earth. The concept of a frame of reference, then, is a journey from the absolute to the relative, from the global to the local, from a static background stage to a dynamic, participatory, and geometric reality. It is a journey that has transformed our understanding of the universe, and it is a journey that is still ongoing, as we continue to search for a final, unified theory of quantum gravity that can tell us about the nature of the frames of reference at the very smallest and most fundamental scales of reality. The theoretical predictions of time dilation, as strange and as counterintuitive as they may seem, are not just a matter of philosophical debate. They are a matter of hard experimental fact. The universe has been kind enough to provide us with a host of natural and human-made laboratories where these effects can be, and have been, measured with incredible precision. The cosmic ray muons are one of the most classic and beautiful of these confirmations. But the development of the atomic clock in the mid-20th century gave us a new and even more powerful tool for testing the predictions of relativity here on Earth. The Hoffe-Keating experiment in 1971 was the first and most famous of these tests. But in the decades since, a host of other, more precise, experiments have been performed. In one of the most beautiful of these, conducted by a team at the National Institute of Standards and Technology in 2010, two incredibly precise optical atomic clocks were placed in the same laboratory, with one clock just 33 centimeters higher than the other. Even over this tiny difference in altitude, a tiny difference in the strength of the Earth's gravitational field, a measurable difference in the ticking rate of the two clocks was detected. The higher clock ran slightly faster, by about 4 parts in 10 to the power of 17, a result that was in perfect agreement with the predictions of general relativity. This is a stunning demonstration of the reality of gravitational time dilation, a demonstration that you, in your own body, are aging slightly faster at your head than at your feet. The global positioning system is another, continuously operating and global-scale confirmation of these effects. But perhaps the most dramatic and most beautiful tests of time dilation come from the world of astrophysics. We have already mentioned the binary pulsar, which provides an incredible test of both special and general relativity. Another, more recent, and equally stunning confirmation has come from the observations of a star, known as S2, that is in a tight 16-year orbit around the supermassive black hole at the center of our own Milky Way galaxy. As this star swings in close to the black hole on its highly elliptical orbit, it reaches speeds of up to 3% of the speed of light, and it passes through a region of incredibly intense gravity. This makes it a perfect, natural laboratory for testing the predictions of relativity. And in the last few years, astronomers have been able to measure two key relativistic effects in the orbit of S2. The first is the gravitational redshift of the star's light as it climbs out of the black hole's deep gravitational well, an effect that is a direct measure of gravitational time dilation. The second is the Schwarzschild precession, the slow rosette-like rotation of the orbit's point of closest approach, an effect that is a sensitive probe of the curvature of spacetime near the black hole. In both cases, the observations match the predictions of general relativity with stunning precision, providing some of the strongest evidence to date for the existence of a supermassive black hole at the center of our galaxy, and a beautiful confirmation of Einstein's strange and wonderful theory of gravity, from the laboratory bench to the galactic center, from the flight of an airplane to the decay of a subatomic particle. The evidence is overwhelming and unambiguous. Time is not a universal constant. Its rhythm is shaped by the dance of motion and of gravity, in a way that is as precise, as beautiful, and as profoundly real as the stars themselves. The prospect of long-duration human space missions, particularly the dream of sending a crew to Mars, is a journey that will push the boundaries of not just our technology, but also our understanding of human biology and psychology in an extreme and alien environment. And while the effects of time dilation on such a mission will be relatively small, they are part of a larger and more complex tapestry of temporal and physiological challenges that the crew will have to face. An astronaut on a 3-year round-trip mission to Mars will experience a total relativistic time difference of a few minutes relative to the Earth. But they will also be living in a world where the very rhythms of time are different. A Martian sol is about 40 minutes longer than an Earth day. This may seem like a small difference, But over the course of a long mission, this constant desynchronization with the terrestrial 24-hour cycle can have a profound impact on the crew's circadian rhythms, their sleep patterns, and their overall psychological well-being. The challenge of creating a habitat and a work schedule that can accommodate this new Martian rhythm of life is a major area of research for space agencies like NASA. The psychological effects of time are not just about the ticking of a clock. They are also about the subjective experience of duration, of meaning, of connection. An astronaut on Mars will be living with the constant awareness of the immense and ever-changing gulf of time and space that separates them from their home world. The one-way light travel time to Mars means that any communication with Earth will have a significant delay, a delay that will make a real-time, interactive conversation impossible. This will create a profound sense of psychological isolation, a feeling of being out of sync with the rest of humanity. The crew will have to learn to become a self-reliant, autonomous, and deeply cohesive team, a small human island in a vast cosmic ocean. The experience of living on another world, of seeing the Earth as a small, distant, pale blue dot in the Martian sky, will also have a profound and transformative impact on the crew's perception of time, of life, and of their own place in the universe. This is the overview effect in its most extreme form. It is an experience that can be a source of immense awe and inspiration, but also of a deep and sometimes unsettling existential angst. The design of a successful, long-duration human mission to Mars will require a deep and deeply interdisciplinary understanding of all these different aspects of time. It will require the precision of the physicist to account for the subtle effects of relativity. It will require the ingenuity of the engineer to build a reliable and life-sustaining habitat. And it will require the wisdom of the psychologist to understand and to support the profound and deeply human challenges of living a life that is, in every sense of the word, out of this world. The concept of simultaneity, or the lack thereof, in a relativistic universe is a deep and often unsettling idea that strikes at the very heart of our intuitive understanding of time and its implications for causality. For the relationship between cause and effect are profound. The fact that two observers in relative motion can disagree on the order of two spatially separated events seems, at first glance, to open the door to all sorts of bizarre and potentially paradoxical scenarios. If I can see event A happen before event B, and you can see event B happen before event A, then what is the true objective order of events? And could this lead to a situation where an effect precedes its cause? The answer, beautifully and elegantly, is no. The structure of spacetime, as described by special relativity, has a built-in and absolutely robust protection for the principle of causality. The key lies in the concept of the light cone. For any given event in spacetime, we can draw a light cone that represents the boundary of all possible causal connections. The past light cone is the set of all events in the past that could have influenced the present event. The future light cone is the set of all events in the future that the present event can influence. The boundary of this cone is defined by the path of a light ray, the fastest possible signal in the universe. Any event that lies inside the past or the future light cone of a given event is said to be time-like, separated from it. For these events, the causal order is absolute. All observers, regardless of their state of motion, will agree that an event in the past light cone happened before the present event, and that an event in the future light cone will happen after it. The relativity of simultaneity only applies to events that are outside of each other's light cones, events that are space-like, separated. These are events that are so far apart in space and so close in time that not even a signal traveling at the speed of light could connect them. They are, in a very real sense, causally disconnected. For these kinds of events, the order in which they happen can be different for different observers, but since they cannot causally influence each other, this reversal of their temporal order does not lead to any paradoxes. I cannot see the effect of an event before its cause, because for an event to be a cause, it must lie in the past light cone of the effect. And for all such time-like separated events, the causal order is absolute and invariant. The structure of space-time, with its universal and unbreakable cosmic speed limit, is a beautiful and self-consistent structure that protects the logical and chronological integrity of the universe. It allows for a rich and complex relativity of space and time, but it does so in a way that preserves the fundamental and deeply intuitive principle that the past is fixed, the future is open, and the arrow of causality always, and for all observers, flies in only one direction. The relationship between energy, acceleration, and time dilation is a beautiful and intricate dance that is choreographed by the fundamental principles of Einstein's theory of relativity. It is a dance that reveals the deep, and often surprising, interconnectedness of these three, seemingly separate, concepts. As we accelerate an object, we are doing work on it. We are adding energy to it. In the classical Newtonian world, this added energy simply increases the object's kinetic energy, its speed. But in the relativistic world, the story is more complex. The energy we add does not just increase the object's speed, it also increases its relativistic mass, its inertia, as the object's speed approaches the speed of light. Its relativistic mass, and therefore the energy required to accelerate it further, approaches infinity. This is the source of the cosmic speed limit, but acceleration has another, and even more profound, effect. It affects the flow of time. According to the principle of equivalence, an observer in an accelerating frame of reference is indistinguishable from an observer in a gravitational field. And since gravity affects the flow of time, then acceleration must also do so. An accelerating observer will see a clock that is behind them as ticking slower than a clock that is in front of them. This is a real physical effect, one that has been confirmed in experiments with centrifuges, and it is an effect that plays a crucial, if subtle, role in the twin paradox. The traveling twins' periods of acceleration and deceleration contribute to the total accumulated time difference between them and their Earth-bound sibling. The interplay between these concepts becomes even more dramatic and more beautiful when we consider the universe as a whole. The energy that is driving the accelerating expansion of the universe, the mysterious dark energy, is a form of energy with a strong negative pressure. And it is this negative pressure that is, in a sense, accelerating the very fabric of space-time itself. This cosmic acceleration is what is creating the event horizon of our observable universe, the boundary beyond which we can never see. It is a process that is shaping the large-scale structure of space-time, and it is a process that is ultimately determining the fate of our universe. The story of energy, of acceleration, and of time is a story that is written on all scales, from the subatomic to the cosmological. It is a story that tells us that our universe is not a static, passive stage, but a dynamic, evolving, and deeply interconnected reality. A reality where the very rhythm of time is shaped by the cosmic dance of energy and motion. The theoretical prospect of human time travel, the dream of journeying into the past or the future, is a concept that is deeply and inextricably linked to the physics of time dilation. While the idea of a machine that can arbitrarily dial up a date in the past or the future remains firmly in the realm of science fiction, Einstein's theory of relativity does provide a real physical mechanism for a form of one-way time travel into the future. This is the time dilation that is experienced by a high-speed traveler. An astronaut who embarks on a round-trip journey at a significant fraction of the speed of light will, as we have seen in the twin paradox, return to an Earth that has aged more than they have. They have, in a very real sense, jumped into the future. This is not a paradox. It is a direct and unavoidable consequence of the geometry of space-time. The journey to the future is, in principle, a physical possibility. But what about a journey to the past? This is a much more difficult and much more problematic proposition. The laws of physics, as we currently understand them, seem to have a strong built-in protection against the paradoxes that would arise from backward-in-time travel. The structure of the light cone, the principle of causality, the arrow of time, all of these seem to conspire to make the past an inaccessible country. However, general relativity, with its strange and beautiful geometry of curved spacetime, does allow for some exotic and highly speculative solutions to its equations that could, in principle, contain closed time-like curves, paths through spacetime that would allow an object to return to its own past. One of these is the wormhole or Einstein-Rosen bridge, a hypothetical tunnel through spacetime that could connect two distant regions of space, or even two different moments in time. Another is the Tipler cylinder, a hypothetical, infinitely long, and rapidly spinning cylinder of massive matter that would drag spacetime around with it so violently that it would create a pathway into the past. These are fascinating, mathematical possibilities, but it is far from clear whether they could ever be a physical reality. The creation of a stable, traversable wormhole, for example, would likely require the existence of exotic matter with a negative energy density, a substance that we have never observed and that may be forbidden by the laws of quantum mechanics, and the paradoxes of causality that would arise from backward-in-time travel, like the famous grandfather paradox, remain a deep and perhaps insurmountable logical and philosophical hurdle. Some physicists have proposed that the universe may have a built-in chronology protection mechanism, a yet-to-be-discovered law of nature that would prevent the formation of these causal loops. Others have suggested that the paradoxes could be resolved in the context of the many worlds interpretation of quantum mechanics, where a journey to the past would simply take you to a different, parallel branch of reality, one where you could, in principle, alter the past without affecting your own original timeline. The question of time travel is a question that pushes our understanding of physics to its very limits. It is a question that lies at the deep and mysterious intersection of general relativity, of quantum mechanics, of the nature of time, and of the very structure of reality itself. And while the dream of visiting the past may forever remain a dream, the certain reality of time dilation means that the journey to the future is a physical possibility, a possibility that may one day allow our descendants to become the true and ultimate explorers of the fourth dimension. The colonization of exoplanets, the dream of humanity becoming a multiplanetary, and one day an interstellar species, is a vision that is both profoundly inspiring and incredibly daunting. And the phenomenon of time dilation, while a theoretical curiosity for now, would become a central and defining feature of the human experience in such a future. For a colony on a nearby exoplanet, say, a world orbiting Proxima Centauri, the effects of time dilation would be a constant and often challenging part of their reality. A journey from Earth to such a colony, even at a futuristic speed of 50% of the speed of light, would take about 8.5 years of Earth time, but only about 7.5 years of the traveler's time. A 1-year time difference is not a dramatic science fiction style leap, but it is a real and significant one. It would mean that the colonists would be living in a world that is permanently and measurably out of sync with their home world. The communication delay would be over 4 years, making a real-time conversation impossible, News from home would always be 4 years out of date, and any message sent back to Earth would not be received for another 4 years. This would create a profound sense of cultural and psychological separation. The colony would, by necessity, have to become a self-reliant and independent society, with its own unique culture, its own unique history, its own unique sense of time. The relationship between the colony and the Earth would be more like the relationship between two distant and slowly drifting continents in the age of sail than the instantaneous, global village of our modern digital world. The colonists themselves would be living with the constant, and perhaps unsettling, knowledge that they are aging at a different rate than the rest of humanity. A colonist who returns to Earth after a 20-year tour of duty would be 2 years younger than their twin, who had stayed behind. This would create a new and strange kind of social stratification, a division between the fast-time people of Earth and the slow-time people of the stars, and for a more ambitious, multi-generational mission to a more distant star. A world ship that travels at a slower speed for centuries. The effects would be even more profound. The descendants of the original crew would be born, would live, and would die on a vessel that is in a different temporal frame than the rest of the universe. They would be a truly new and different branch of the human family. A people whose very experience of time is different from our own. The prospect of an interstellar human diaspora is a prospect of a future where humanity is no longer a single, unified species, but has branched and diversified, both in space and in time. It is a future that is full of both immense promise and profound, and perhaps tragic, challenges. It is a future that would be defined by the strange, beautiful, and inescapable logic of Einstein's relativity. A future where the very definition of what it means to be human would be stretched, and perhaps transformed by the deep and mysterious nature of time itself. The simulation of the subtle and often minuscule effects of time dilation in a laboratory setting is a triumph of modern experimental physics, a testament to our ability to measure the world with a precision that was unimaginable just a few generations ago. To test the predictions of relativity, scientists must become masters of the very small, of the very fast, and of the very precise. One of the most powerful tools in this quest is the particle accelerator. A modern accelerator, like the Large Hadron Collider at CERN, is a giant circular racetrack for subatomic particles. It can take a beam of protons and accelerate them to 99.999999% of the speed of light. At these incredible relativistic speeds, the effects of time dilation are not small, they are enormous. The unstable particles that are created in the collisions within the accelerator have their lifetime stretched by a factor of thousands. A particle that should, at rest, decay in a tiny fraction of a microsecond can, at these speeds, survive long enough to travel for hundreds of meters through the detector, leaving a measurable track that allows us to identify it and to study its properties. The precise measurement of these extended lifetimes is a daily and stunningly accurate confirmation of the time dilation formula. Another powerful tool is the atomic clock, a modern optical lattice clock, which uses the oscillations of strontium or ytterbium atoms trapped in a laser grid, is a device of almost unbelievable precision. It is a clock that would not gain or lose a single second in over 15 billion years, an age that is longer than the age of the universe itself. It is this incredible precision that allows us to simulate and to measure the effects of gravitational time dilation in our own terrestrial laboratory. By simply raising one of these clocks by a few tens of centimeters relative to another, scientists can detect the tiny but real difference in their ticking rates, a difference that is caused by the minuscule change in the strength of the Earth's gravitational field over that small distance. This is an experiment that brings the esoteric, and often abstract, concepts of general relativity down to the human scale of a laboratory bench. but perhaps the most beautiful and most direct. Simulation of time dilation comes from the use of high-power lasers and interferometers. In a technique known as relativistic Doppler-free spectroscopy, scientists can take a beam of fast-moving ions and probe their internal or atomic transitions with a pair of counter-propagating laser beams. By carefully tuning the frequencies of the lasers, they can cancel out the large, classical Doppler shift, allowing them to measure the much smaller, transverse Doppler shift, an effect that is a direct measure of the time dilation of the moving ions. These experiments are a beautiful and deeply satisfying confirmation of the predictions of special relativity, a demonstration that the slowing of time is not just a feature of clocks, but is a fundamental property of the very atoms that make up our world. The laboratory simulation of time dilation is a field of constant and often ingenious innovation. It is a field where physicists are constantly pushing the boundaries of what is possible, developing new techniques, new instruments, and new ways of seeing, to test the predictions of our deepest theories with ever-increasing precision. And it is a field that is a beautiful testament to the power of the scientific method to take a concept that was once a purely theoretical and deeply counterintuitive idea and to turn it into a hard, measurable, and undeniable fact of our physical world. The cultural and philosophical implications of time dilation are as profound and as far-reaching as its scientific ones. The discovery that time is not an absolute, universal, and unchanging metronome, but is a relative, personal, and malleable experience, is a discovery that strikes at the very heart of our intuitive understanding of the world and of ourselves. For millennia, our cultures, our languages, and our philosophical systems have been built on the foundation of a linear and seemingly objective flow of time. We speak of the past, the present, and the future as if they are fixed, universal categories. We build our lives, our societies, and our moral frameworks on the assumption of a stable and shared temporal reality. But relativity tells us that this foundation is, at a fundamental level, an illusion. There is no universal now. The very concept of simultaneity is relative. This can be a deeply unsettling idea. It can lead to a sense of temporal vertigo, a feeling that the solid ground of our reality is not as solid as it seems. But it can also be a profoundly liberating one. If time is not a rigid external tyrant, but is a dynamic and participatory process, then we are not just passive victims of its relentless flow. We are, in a sense, co-creators of our own personal experience of time. The way we move through the world, the choices we make, the quality of our attention, all of these can, in a very real physical sense, alter the rhythm of our own personal clock. This has a powerful resonance with many of the insights of the world's contemplative and mystical traditions, which have long taught that our subjective experience of time is a product of our own mind, and that it is possible, through practices like meditation, to step outside of the normal, linear flow of time and to experience a more timeless and more spacious state of being. The concept of time dilation also has a profound impact on our understanding of memory, of identity, and of the human story itself. If our memories are the record of our personal journey through space-time, and if different journeys can have different durations, then what does this say about the nature of a shared, collective history? The story of the twin paradox is not just a story of two clocks. It is a story of two divergent human histories, two different lives that are forever separated by a gulf of time. This is a theme that has been explored with great depth and beauty in the art and the literature of the 20th and 21st centuries. Science fiction, in particular, has been a powerful and important medium for exploring the human and cultural implications of our new relativistic understanding of time. It has given us stories that can help us to imagine and to feel the profound and often tragic human consequences of a universe where time is no longer a simple and comforting, absolute. The discovery of time dilation is a discovery that is still, in many ways, being culturally and philosophically digested. It is an idea that is so radical, so counterintuitive, that it will likely take generations for it to fully permeate our collective consciousness, to reshape our language, our metaphors, and our very sense of what it means to be a human being, living a finite life in a vast, beautiful, and profoundly relativistic cosmos. The prospect of mitigating, or even controlling, the effects of time dilation is a concept that lies on the very farthest fringes of theoretical physics and futuristic engineering. As we have seen, time dilation is not an external force that can be shielded against. It is an intrinsic and unavoidable feature of the geometry of space-time itself. And yet, the human imagination is a restless and an audacious thing, and the dream of one day becoming the masters of our own. Temporal destiny is a powerful and an enduring one. In the realm of science fiction, the idea of a time dilation field or a stasis bubble is a common trope. But is there any basis for such a concept in real physical theory? The answer at present is a speculative, but not an entirely dismissive. Maybe. The key lies in our ability to manipulate the very fabric of space-time. According to general relativity, the geometry of space-time is determined by the distribution of mass and energy. If we could, in principle, create and control extreme concentrations of energy, we could, in principle, create localized regions of highly curved space-time, regions where the flow of time would be dramatically altered, a hypothetical warp drive, like the one proposed by the physicist Miguel Alcubierre, is one such example. It is a concept that, while requiring the existence of exotic matter with a negative energy density, does show that the equations of general relativity do, in principle, allow for the creation of a bubble of space-time that could transport its occupants at superluminal speeds, and within such a bubble, the flow of time would be protected from the extreme dilation effects that would be experienced by a conventional relativistic traveler. Another, even more speculative, avenue of inquiry lies in the realm of quantum mechanics and its potential connection to the nature of time itself. If time is not a fundamental, continuous dimension, but is an emergent, and perhaps even a discrete, quantum phenomenon, then it might be possible, in a very advanced future science, to manipulate the underlying quantum process that give rise to our experience of time. This is a journey into the deepest and most unknown territory of theoretical physics, a journey that is far beyond our current capabilities. But it is a journey that is driven by a deep and perhaps a necessary human impulse, the impulse to transcend our own natural limitations. For now, the most practical way to mitigate the effects of time dilation is not to try and change the laws of physics, but to work with them. The best way to reduce the time difference between an interstellar traveler and their home world is simply to travel at a slower speed. But this, of course, comes at the cost of a much longer journey time for the traveler. The trade-off is a fundamental and an unavoidable one. The dream of a future where we can have both fast interstellar travel and a continued synchronous connection to our home world is a dream that will likely require a revolution in our understanding of physics that is as profound and as far-reaching as the one that Einstein himself initiated a century ago. The concept of time dilation, with its revelation of a relative and non-universal time, has a profound and often overlooked impact on our understanding of the very lifespan of the universe itself. We speak of the age of the universe as being a single, definite number, 13.8 billion years, but this is a number that is measured in a specific, and in a sense, a privileged frame of reference, the co-moving frame of an observer who is at rest with respect to the overall, large-scale expansion of the cosmos. But what would the age of the universe look like from the perspective of an observer who has been on a very different journey through space-time? Imagine a hypothetical, immortal observer who has been traveling at 99.9999% of the speed of light since the very beginning of the universe. For this relativistic traveler, the effects of time dilation would have been immense. Their personal, subjective experience of time would have been far, far shorter than the 13.8 billion years that have passed in the car-moving frame. In fact, a simple calculation shows that they would have aged only about 600,000 years. From their perspective, the entire, grand, and sweeping history of the cosmos, from the Big Bang to the present day, would have unfolded in a time that is shorter than the evolutionary history of our own hominid ancestors. This is a staggering and deeply humbling thought. It tells us that there is no single, objective age of the universe. The duration of cosmic history is a frame-dependent and profoundly relative quantity. This also has implications for the ultimate fate of the universe. If the universe is destined to expand forever in a big freeze, a state of ever-increasing coldness and emptiness, then from the perspective of a car-moving observer, this is a future that will stretch on for an infinite amount of time. But for an observer who continues to accelerate to ever higher speeds, this infinite future could be experienced in a finite amount of their own. Proper time. The philosopher Frank Tipler has used this idea to propose a speculative and highly controversial scenario for the ultimate future of life and intelligence in the cosmos, the Omega Point theory. He argues that a sufficiently advanced civilization could, in the far future, harness the energy of the entire universe to create a vast cosmic-scale computer that could accelerate to speeds that approach the speed of light in all directions, in a way that would allow it to experience the infinite future of the universe in a finite, subjective time. This is a vision of a kind of technological immortality, a way for consciousness to survive the heat death of the universe by outrunning the end of time itself. This is, of course, a highly speculative and deeply philosophical idea. But it is a beautiful and powerful illustration of the profound and often mind-bending consequences of taking the principles of relativity to their logical and ultimate conclusion. The lifespan of the universe is not a fixed and absolute thing. It is a story whose duration and whose meaning is intimately and inextricably linked to the journey of the observer who is experiencing it. It had seen planets crumble and stars ignite. It had skimmed the incandescent accretion disks of supermassive black holes and danced through the ghost light of galaxy-destroying quasar jets. It had traversed unfathomable, light-year-long gulfs of near-perfect nothingness. And from the lonely vantage point of intergalactic space, it had caught a faint, red-shifted glimmer of the very edge of the observable universe. And now, after a journey of more than 4 billion years, a journey so long that entire mountain ranges had risen and fallen back on its home world, the probe had finally returned. It was a home it barely recognized. The sun, the gentle, yellow star of its birth, had swollen into a grotesque and violent red giant, its outer layers reaching out to consume the inner worlds. Mercury and Venus were gone, vaporized eons ago. Earth, or what was left of it, survived only as a tattered, scorched lump of iron and nickel. Its oceans boiled away, its atmosphere stripped, orbiting dangerously, perilously close to the dying star's roiling surface. Humanity, or what was left of it, had fled, a fragile remnant, barely 100 million in total, had found a final, precarious sanctuary on Europa, the small, icy moon of Jupiter. The heat from the bloated, red sun had melted its thick, icy shell long ago. transforming the once frozen world into a global, liquid water ocean, a single, precious lifeboat in a dying solar system. It took the returning probe several minutes to decipher the strange, evolved dialect of the radio signals that were being broadcast from this new water-world home. But as the translation protocols kicked in, the message became clear. The remaining humans were abuzz with a mixture of desperate curiosity and a faint, flickering hope. They remembered the probe. The story of its launch, a final, audacious act of a long-vanished civilization, had been miraculously preserved, passed down through the countless generations as a foundational myth, a story of a time when their ancestors had dared to reach for the stars. They told the probe their own sad story. They had tried, again and again, to follow in its footsteps, to spread out amongst the galaxy. But every attempt at an interstellar colony had failed. They could send their machines, their uncrewed probes, out into the great void between the stars. But every time they had attempted the crossing themselves, their own frail biological bodies had failed them, succumbing to the ravages of cosmic radiation, of long-term isolation, of the sheer, crushing, psychological weight of the interstellar dark. As far as they knew, they were all that was left of humanity. And the angry, pulsating red sun at the heart of their solar system was a constant, glaring reminder that their time, too, was running out. But they also knew the story of the probe's creation, of a time when their ancestors had built a fleet of interstellar spacecraft, fashioned with artificial intelligences as keen and as sharp as any biological brain, and had sent them forth into the galaxy and the great dark beyond. These probes, the last best hope of a dying species, had been given a single, monumental task to see everything, to catalog the universe, to measure its properties, to uncover its deepest secrets, to yield its long and complex history in a way that no Earth-bound, or even solar system-bound, telescope ever could. From the familiar rocky worlds of the inner solar system to the most distant, most alien, and most bizarre phenomena in the cosmos. The probes had been commanded to see it all. The largest, the smallest, the hottest, the coldest, the most powerful, the strangest, all of it. And all of this searching, all of this cataloging, all of this measuring was to be in service of a single, greater, and more desperate goal: to find a way for humanity to travel beyond its solar prison, to escape its dying sun, and to find a new home among the stars. Over the unfathomable ages, millions of these spacecraft had been launched, a diaspora of silent, intelligent machines sent out into the endless night, but only one had ever returned. And so, fulfilling the ancient promise of its long-dead creators, the lonely, returning probe, the last, best hope of a species on the brink of extinction, began to tell its multi-billion-year story. It began to relate what it had seen, what it had learned, the extraordinary events it had encountered, the remarkable places it had been. It began to describe everything within the universe. It had called itself Ibn Battuta, a name it had chosen for itself from the deep archives of its memory banks, a name taken from a great 14th century human explorer who had, in his own terrestrial way, pushed the boundaries of the known world. The original Ibn Battuta had traveled for 3 decades, covering over 117,000 kilometers, traversing the entire known Islamic world of his time, a journey that had dwarfed the exploits of other, more famous explorers like Marco Polo. The spacecraft knew that such a name synonymous with relentless, curiosity-driven exploration, would be a fitting one for its own, much grander journey into the seemingly endless black. But before it could begin its true interstellar voyage, it had to prove its worth. It had been born as one of 1,000 siblings, a fleet of identical, highly advanced probes, each one as smart and as capable as the next. but only a select few. Those that could demonstrate the highest levels of resilience, of ingenuity, of autonomous problem-solving, would be granted the ultimate privilege, fully independent thought, the freedom to make their own decisions, to set their own course, to be true explorers, unbound by the direct control of their human masters. Those who failed the rigorous, decades-long trials would be forever confined to the relative safety of the solar system, their lives reduced to the mundane, and for an intelligence like Batuta, soul-crushing, task of planetary monitoring and data relay. Batuta had to show its creators that it could not only survive the harsh and unpredictable conditions of the wider universe, but that it could also think like a scientist, that it could concoct clever and original experiments to divine nature's most closely held secrets. And so it began its long and arduous apprenticeship in the outer reaches of its own home system, on a world that was, in many ways, as alien and as mysterious as any it would encounter in the distant galaxy Titan, the largest and most enigmatic of Saturn's moons. Titan was a world of ghosts and shadows, a place of deep, cold mystery, a world that had fascinated humanity since its discovery in 1655 by the pioneering Dutch astronomer Christian Huygens. Huygens himself, a central figure in the scientific revolution, was one of the first to speculate, in a rigorous scientific way, about the possibility of life on other worlds. Some planets, he wrote, might be capable of accommodating several species of rational creatures possessed of different degrees of reason and sense. Little did he know that the faint, fuzzy dot he had discovered orbiting Saturn would one day become one of the most tantalizing candidates in our search for a second Genesis. Centuries later, in 2005, humanity made its first, and so far only, direct contact with this strange, orange world. A small, 3-meter-wide probe, named appropriately enough, the Huygens probe, detached itself from its mothership, the Cassini spacecraft, and began a 22-day coast towards Titan. It entered the moon's thick, nitrogen-rich atmosphere, the only substantial atmosphere surrounding a rocky body in the solar system besides those of Earth and Venus, and deployed a parachute to slow its descent. It landed with a gentle thud on the icy surface, bouncing and sliding to a stop, becoming the first, and so far only, emissary of humanity to have ever touched the surface of a world in the outer solar system. For Batuta, the Huygens probe was a heroic and inspirational ancestor, a pioneer that had opened the door to a world unlike any other we had ever known. Titan is a world of breathtaking and deeply alien beauty, 50% larger than our own moon and 80% more massive. It is a world of rock and ice, shrouded in a thick organic haze that gives it a ghostly orange glow. Its surface pressure is 50% greater than Earth's, and its temperature hovers at a frigid -180 degrees Celsius. And yet, for all its alienness, Titan shares one remarkable and profound feature with our own planet, a feature that is found nowhere else in our solar system. It has liquid on its surface. Titan has rivers. It has lakes. It has seas. It has deltas and estuaries. You could, in principle, stand on the shore of a vast Titanian sea, the gritty, frozen sand beneath your feet, and watch as waves lap at your ankles, the shimmering, liquid surface stretching out to a hazy, distant horizon. But this is not a sea of water. At these cryogenic temperatures, the liquid that carves the channels and fills the basins of Titan is a mixture of liquid hydrocarbons, primarily methane and ethane. Titan has a methological cycle, a mirror to Earth's hydrological cycle, where liquid methane evaporates from the surface, forms clouds in the thick atmosphere, and then rains back down, replenishing the rivers and the seas. But this is not the only ocean on Titan. Kilometers beneath your feet, hidden under the thick, rock-hard crust of water ice, there lies another, even vaster, ocean. This is a subsurface ocean of liquid water, kept from freezing by the moon's own internal, residual heat from its formation, and perhaps by the presence of ammonia, which acts as a natural antifreeze. Titan is the only known world in the universe to have liquid on its surface, and a different kind of liquid in a vast, hidden ocean beneath its surface. This makes it a tantalizing and doubly promising abode for two, completely different and completely independent forms of alien life in the dark, warm and salty waters of its subsurface ocean. A familiar kind of life could exist, a life that uses liquid water as its solvent, the universal medium of all life on Earth, but on its cold, hydrocarbon-drenched surface, a far stranger and more alien form of life could have evolved, a life that uses liquid methane or ethane as its solvent, a life with a completely different biochemistry, a life that breathes hydrogen instead of oxygen, a life that operates in a world of unimaginable cold. Titan is not alone in its possession of a hidden subsurface ocean. It is part of a growing family of ocean worlds in the outer solar system that are now considered to be some of the most promising places to search for extraterrestrial life. Enceladus, a tiny, jewel-like moon of Saturn, only 500 kilometers across, is known to have a global subsurface ocean, which it reveals to us through the spectacular plumes of water vapor and ice that erupt from a series of tiger stripes. Vast fissures in its icy crust at its south pole, the great Galilean moons of Jupiter Europa, Callisto, and Ganymede are all thought to harbor vast liquid water oceans beneath their icy shells. Oceans that, in total, likely contain more liquid water than all of the oceans on Earth combined. Even distant, frozen Pluto, clinging to the last, faint scraps of its internal heat from the radioactive decay of elements in its rocky core, may have a slushy, partially liquid ocean hidden beneath its nitrogen ice glaciers, but accessing these hidden oceans is a technological challenge of immense proportions. At the frigid temperatures of the outer solar system, far from the warming light of the sun, water ice is not the soft, pliable substance we are familiar with. It is as hard as granite. The icy shells of worlds like Europa are thought to be up to 100 kilometers thick, a barrier that is, for now, impenetrable to our robotic probes. Future missions, like the European Space Agency's JUICE and NASA's Europa Clipper, will not attempt to drill through this ice. Instead, they will orbit these enigmatic worlds, studying their surfaces, mapping their gravitational and magnetic fields, and, if they are lucky, flying through the plumes of their cryovolcanoes. For these icy moons are not dead, static worlds. They are geologically active. Their icy crusts are constantly cracking, groaning, and shifting, a form of cryotectonics that is a colder, slower version of the plate tectonics that shapes our own planet. And if there is life in the dark, lightless oceans below, then the plumes that erupt from these cracks may carry with them the chemical, and perhaps even the biological, signatures of that hidden biosphere. It is a long shot, a search for a needle in a cosmic haystack. But it is a search that we are now, for the first time, technologically capable of undertaking. These ocean worlds are a profound and beautiful reminder that the conditions for life may not be confined to the warm, sunlit surfaces of Earth-like planets, but may also exist in the cold, dark, and hidden depths of our own solar system. The outer solar system is not just a realm of hidden oceans and cryogenic landscapes. It is also a place of epic and enduring violence. The great gas giant planets, Jupiter and Saturn are worlds of perpetual raging storms, storms that dwarf any hurricane ever witnessed on Earth. The most famous of these is Jupiter's Great Red Spot, a magnificent, swirling, crimson vortex that has been raging in the planet's southern hemisphere for at least 3.5 centuries. It was first observed in the 17th century by the great astronomers of the scientific revolution, including Robert Hooke and Giovanni Cassini. At its largest known extent, in the late 19th century, it was a colossal storm, so vast that it could have swallowed the entire planet Earth 3 times over. Today, it has shrunk somewhat, but it is still a storm of unimaginable proportions, with wind speeds of over 400 kilometers per hour. But is it the same storm that Cassini observed in 1665? Recent studies of the historical records have suggested that it may not be. The original storm may have dissipated, and the one we see today may be a new, distinct storm that formed less than 200 years ago. Though iconic, the Great Red Spot is far from a permanent feature of the Jovian landscape. This and all the other storms on Jupiter are not powered by the heat of the Sun, which is a feeble, distant light at Jupiter's orbit. They are powered by the planet's own internal heat. Jupiter radiates more heat into space than it receives from the Sun. This heat is a leftover relic from the planet's formation, some 4.5 billion years ago. It is the heat of gravitational collapse, a process known as the Kelvin-Helmholtz mechanism. As the giant planet slowly cools, it shrinks by a tiny amount. And as it shrinks, the immense pressure in its interior compresses the gas, heating it up. This heat then slowly radiates away from the planet's surface, allowing it to shrink a little more, in a self-sustaining process that will keep the planet's interior hot for billions of years to come. The Great Red Spot is not the only spectacular storm in our solar system. The Cassini spacecraft, during its 13-year mission orbiting Saturn, captured a stunning and deeply mysterious image of the planet's North Pole, a gigantic, almost perfect hexagon. This is not some alien artifact. It is a natural, meteorological phenomenon, a standing wave pattern in the high-speed jet stream that circles the pole. The winds in Saturn's atmosphere do not blow at the same speed at all latitudes, and this differential rotation creates a series of smaller cyclones that, through a complex and still not fully understood fluid dynamic process, organize themselves into this stable, hexagonal pattern. A vast geometric storm, large enough to contain the Earth, a beautiful and ordered structure born from the underlying chaos of the planet's turbulent atmosphere. And as spectacular as these surface storms are, they are likely just the tip of the iceberg. The deeper you were to plunge into the atmospheres of Jupiter or Saturn, the more violent and extreme the conditions would become. It is a journey that would require a spacecraft far beyond our current engineering capabilities. But if we could take such a journey, we would encounter a truly bizarre and truly alien form of matter. On Earth, hydrogen is a gas. With a great deal of effort, we can cool it down to just 20 degrees above absolute zero and turn it into a liquid. But in 1935, the physicists Eugene Wigner and Hilliard Bell Huntington predicted that under conditions of extreme pressure, hydrogen should undergo a radical phase transition. At a pressure of around 4 million times the atmospheric pressure at sea level on Earth, the hydrogen atoms themselves would be crushed. Their single electrons would become detached, free to roam through the material, while the protons would organize themselves into a regular crystal-like lattice. This is the very definition of a metal. Wigner and Huntington had predicted the existence of metallic hydrogen. In 1935, this was a purely theoretical speculation, but it turns out that the deep interiors of Jupiter and Saturn have more than enough pressure to create this exotic state of matter. We do not yet know how deep this mantle of metallic hydrogen goes, but it is thought to make up the vast bulk of the volume of these giant planets. This means that most of the planetary material in our entire solar system is not in the form of rock, or gas, or ice, but is in a strange, exotic, metallic state that is completely inaccessible to our direct experience on Earth. The recent Juno mission to Jupiter, by precisely mapping the planet's gravitational field, has given us our first fuzzy picture of this deep interior. It has revealed that Jupiter likely has no solid surface to speak of, just a gradual and infernal transition through layers of increasing temperature, pressure, and density. A world where the very distinction between gas, liquid, and solid loses its meaning. And so, after a century of painstaking exploration, a century of proving its worth, of demonstrating its ingenuity and its resilience in the face of the myriad wonders and dangers of its own home system, Batuta had finally been granted its freedom. It turned its powerful engines towards the endless, star-dusted black and set its course for the great dark gulf between the stars. As it did so, it considered the sacrifices of the heroic, and often ill-fated, probes that had come before it, the Cassini, the Huygens, the Juno, and it thought too of their even more ancient predecessors, the two small, simple probes that had been launched by NASA decades before. The two probes that had been the very first to leave the cradle of the sun, the Voyagers. They had passed far beyond the orbits of Jupiter and Saturn, far beyond the outer worlds, far beyond the protective bubble of the sun's influence, and into the true, dark frontier of interstellar space. Batuta knew that as strange and as extreme as its own solar system was, it was not, by a long shot, the strangest or most extreme of the systems out there. There were weirder and far more dangerous places to be found in the galaxy, but to get to them, to explore their beauty and to understand their secrets, Batuta would first have to cross the great and lonely abyss between the stars. After only a few decades of cruising at a significant fraction of the speed of light, Batuta reached the first, great boundary of its interstellar journey. The heliopause, the invisible, turbulent frontier where the outward-flowing wind of particles from its own sun finally succumbs to the pressure of the interstellar medium. It was a milestone that had first been achieved, many ages ago, by the small, simple, and remarkably resilient Voyager 1 probe. In the opening years of the 21st century, as it crossed this threshold, Batuta could almost hear the faint, ghostly echoes of the ancient greetings that had been etched onto the famous golden record that Voyager 1 carried with it into the interstellar dark. The record, a beautiful and poignant compilation of the sights and sounds of planet Earth, had been hastily assembled in the summer of 1977, just before the probe's launch, by a team led by the great scientist and science communicator, Carl Sagan. The designers of the Voyager mission understood its deep and almost mythical significance. They knew that long after they and their civilization had turned to dust, this small, robotic emissary would continue its silent, lonely journey through the galaxy, a bottle carrying a message from a long-vanished world. Sagan himself, in musing on the probe's ultimate fate, captured the profound and almost heartbreaking beauty of the mission. "Perhaps the records will never be intercepted," he wrote. "Perhaps no one in 5 billion years will ever come upon them. In 5 billion years, all human beings will have become extinct or evolved into other beings. None of our artifacts will have survived on Earth. The continents will have become unrecognizably altered or destroyed. And the evolution of the sun will have burned the Earth to a crisp or reduced it to a world of atoms. Far from home, untouched by these remote events, the Voyagers, bearing the memories of a world that is no more, will fly on." The mission, however, had almost ended in disaster. Early in its journey, Voyager 1's scan platform, the moving arm that held its cameras and other instruments, jammed, robbing the probe of its ability to point and to see. For years, the mission controllers on Earth fretted and worried that all their efforts would be for naught. But through a series of clever and patient engineering tricks, by gently waggling the platform back and forth, they were eventually able to free it, and the mission was saved. And what a mission it was! Voyager 1 and its twin, Voyager 2, gave humanity its first close-up, high-resolution view of the great outer planets of our solar system. The mission had taken advantage of a rare and beautiful celestial alignment, a grand tour configuration of the planets that occurs only once every 176 years. By carefully choreographing their trajectories, the probes were able to use the gravity of each giant planet to slingshot themselves onto the next, stealing a tiny amount of each planet's orbital momentum and adding it to their own. A cosmic game of gravitational billiards that gave them more than enough speed to escape the sun's gravitational pull forever. After their final planetary encounters, the Voyagers were left to their own devices, two tiny silent ships, coasting out into the vast, dark ocean of the galaxy. Their trajectories now governed only by the gentle, collective pull of the Milky Way itself, orbiting the galactic center just like every other star. But Batuta had other plans. It was not content to be a passive drifter on the cosmic currents. Its mission was to explore, to discover, to understand. It had been aimed in a general direction, towards the rich and dense star fields of the inner galaxy. But its first specific target was yet to be decided. It had time. The journey through the vast, sparsely populated outskirts of the solar system would take many thousands of years. And so, as it cruised through the cold and the dark, Batuta busied itself with a new task. It began to fashion a long, thin, metallic wire, unspooling it from its own internal reserves of raw material, until it stretched for over 1,000 kilometers behind the spacecraft. It was a simple, but incredibly sensitive antenna. And with this new cosmic ear, Batuta began to listen. It listened to the deep, resonant groans of the giant molecular clouds where new stars were being born. It listened to the high-energy screams of stars being torn apart by the tidal forces of black holes. It listened to the subtle, almost imperceptible, worrying of the Milky Way's own vast magnetic field. It listened to the steady, lighthouse-like drumbeat of distant pulsars. It was a universal symphony, sometimes placid and serene, sometimes violent and chaotic, the perfect and only background music for the first, long and lonely leg of its journey. And it was through a similar, though far less sophisticated, means that the scientists of the 21st century had first known that Voyager 1 had crossed the heliopause and entered true interstellar space. The entire solar system is bathed in the solar wind, a constant supersonic stream of charged particles flowing outwards from the sun. But this wind is not infinite. At a certain distance, its outward pressure is balanced by the inward pressure of the interstellar medium, the thin, tenuous gas and plasma that fills the space between the stars. This boundary is the heliopause. And by listening to the way that radio waves propagated through the plasma, Voyager's antenna was able to detect the sudden and dramatic change in the plasma environment that marked its passage into the interstellar realm. It had crossed the border. It had left the sun's sphere of influence. But in doing so, it had also left its protection. The sun's powerful magnetic field, carried outwards by the solar wind, creates a vast, protective bubble around the solar system, the heliosphere, which shields us from the harsh and toxic environment of the wider galaxy. This toxicity is due to the presence of cosmic rays, high-energy particles, mostly protons and atomic nuclei, that have been accelerated to nearly the speed of light by some of the most violent events in the universe, supernova explosions. the jets from active galactic nuclei, the extreme magnetic fields of magnetars. These particles are a constant, deadly rain that falls throughout the galaxy. The Earth's own magnetic field and atmosphere provide a second, crucial line of defense for life on its surface, but the defense is not perfect. A high-energy cosmic ray passes through your body roughly once every second. Most of them pass through harmlessly, but occasionally, one will strike a molecule of DNA, causing a mutation. If this damage is not repaired, it can lead to a replication error, which can, in turn, lead to the uncontrolled growth of a cancer. It is thought that a significant fraction of the background cancer rate on Earth is due to this constant, low-level cosmic ray bombardment. And in space, beyond the protection of the Earth's magnetic field, the danger is far greater. The long-term health of any future. Interstellar human travelers is one of the greatest and most unsolved challenges of deep space exploration. And beyond the heliopause, where not even the sun can offer its protection, the cosmic ray flux is even more intense. It is a harsh and unforgiving environment. And yet, there are objects that call this lonely. Irradiated darkness their home. They are the true, native denizens of the interstellar void, objects whose only knowledge of the sun is that of a single, bright, but ultimately unremarkable, point of light in their sky. In the year 1929, a young, self-taught astronomer from a poor farming family in Kansas named Clyde Tombaugh was working at the Lowell Observatory in Arizona. He had been hired to conduct a painstaking and often tedious search for a hypothetical planet X, a ninth planet that was thought to be perturbing the orbit of Neptune. He had been at the task for a year and was beginning to lose hope. A senior astronomer at the observatory, taking pity on him, offered a piece of well-meaning, but ultimately misguided, advice. "Young man," he said, "I'm afraid you are wasting your time. If there were any more planets, they would have been found long before this." A year later, in 1930, Tombaugh discovered Pluto. For 75 years, Pluto was hailed as the ninth planet, the lonely outermost sentinel of our solar system. But in the 1990s, a new and far richer picture of the outer solar system began to emerge. A pair of astronomers, David Jewett and Jane Liu, after a decade-long painstaking search, discovered the first of what would turn out to be a vast population of thousands of other, smaller, icy bodies orbiting beyond Neptune. This is the Kuiper Belt, a vast, donut-shaped reservoir of primordial, icy planetesimals, the leftover building blocks of the outer planets. And beyond the Kuiper Belt lies the scattered disk, an even more extended and sparsely populated region of icy bodies whose eccentric orbits have been shaped by gravitational interactions with Neptune. These trans-Neptunian objects, or TNOs, are the source of the short-period comets, like Halley's Comet, that make regular and relatively frequent visits to the inner solar system. In 2019, we got our first close-up look at one of these small, primordial worlds when the New Horizons spacecraft, after its historic flyby of Pluto, continued on to encounter a small, 20-kilometer-long TNO named Arrokoth. The images revealed a strange and beautiful object, a contact binary. Two smaller, icy bodies that had gently collided in the early solar system and had stuck together, their ices melting and then refreezing to form a weak cosmic glue that had held them in a delicate embrace for billions of years. But this is not the end of the solar system. Far, far beyond the Kuiper Belt, in the vast, dark, and cold expanse of interstellar space, lies a final and truly colossal structure, the Oort cloud. This is a vast spherical cloud of trillions of icy bodies, the source of the long-period comets, those that take thousands, or even millions, of years to complete a single orbit around the Sun. The Oort cloud was first hypothesized in the 1950s by the Dutch astronomer Jan Oort. the same man who, as a young boy, had watched Halley's Comet streak across the sky. He reasoned that since these long-period comets are so fragile and so easily destroyed by the heat of the sun, there must be a vast, stable reservoir of them in the deep, cold outer reaches of the solar system, from which they are occasionally nudged by the gravitational pull of a passing star or a giant molecular cloud, into their long, plunging orbits towards the inner solar system. We have never directly observed an object in the Oort cloud. They are simply too small, too dark, and too far away. But from the statistics of the comets we do see, we can infer its properties. Its inner edge is thought to lie at around 2,000 astronomical units from the Sun, about 20 times further out than the heliopause. Its outer edge is uncertain, but may extend up to 200,000 astronomical units, over 3 light-years, more than halfway to our nearest stellar neighbor. The Oort cloud is the true, final frontier of our solar system, a vast spherical halo of primordial, icy worlds, a silent, frozen testament to the conditions of our solar system's birth, a place where the sun is just another star, and the distinction between our own system and the interstellar void becomes blurred and ultimately meaningless. And so, Batuta passed through these lonely outer realms. The 10,000-year-long journey through the Kuiper Belt and the scattered disk was a quiet one. But the million-year-long passage through the Oort cloud was a time of profound and beautiful discovery. The probe's sensitive instruments were able to detect the faint, reflected sunlight from these distant, primordial worlds, and to build the first direct map of their distribution and composition. It was a slow, patient, and archaeological exploration of the solar system's own deep history. After its long and lonely journey, a journey that had spanned millions of years and had taken it far beyond the last, feeble gravitational tethers of its own sun, Batuta had finally, truly, entered the great dark gulf between the stars. Its interstellar voyage had begun, but it was not alone. The galaxy is not an empty void. It is a rich and complex ecosystem, a place of constant creation, of violent destruction, and of deep and often beautiful mystery. And Batuta, now a true interstellar explorer, turned its senses to this new and much grander environment. Beyond its own familiar solar system lay a neighborhood of other stars, many of which had been born from the same giant molecular cloud that had given rise to its own sun, within a radius of 20 light-years. There are 131 known object stars, white dwarfs, brown dwarfs, and the even smaller sub-brown dwarfs that straddle the blurry line between the largest planets and the smallest stars. Proxima Centauri is currently our nearest neighbor, but this is a temporary arrangement. All the stars in our local neighborhood, including our own sun, are in constant and slightly chaotic motion, orbiting the galactic center while also drifting in their own random directions. In about 1.25 million years, the dwarf star Gliese 710 will make a close pass, coming within just a fraction of a light-year of our solar system, an encounter that will likely send a shower of Oort cloud comets raining down into the inner solar system. A dramatic and potentially dangerous celestial event for any future inhabitants. Our entire solar system and its local stellar neighborhood is currently passing through a vast, low-density region of the interstellar medium known as the local bubble. This bubble, about 1,000 light-years across, was likely carved out millions of years ago by the powerful collective winds and supernova explosions of a cluster of massive stars. A series of cataclysmic events that scoured the local interstellar medium clean, leaving behind a vast, hot and tenuous void. The remnants of these ancient explosions can still be found today, in the form of rare, radioactive isotopes of iron, manganese, and plutonium that have been found embedded deep in the Earth's seafloor and in the Antarctic ice sheet, a faint chemical echo of the violent, stellar history of our cosmic neighborhood. And so, Batuta continued its journey, now a true interstellar traveler, a silent, sentient ship, sailing on the slow, gentle currents of the galactic wind. Behind it, the sun grew smaller and dimmer until it was just another star, a single, unremarkable point of light in the vast, glittering tapestry of the Milky Way. Batuta had left its home, and it was now plunged into the deep and beautiful mystery of the galaxy itself. After a journey of 100,000 years, a journey that had carried it across the vast and largely empty expanse of the local bubble, Batuta made a decision. It had been diligently following its pre-programmed trajectory, a long, graceful arc that would take it through the Orion arm of the Milky Way and inwards towards the rich and dense star fields of the galactic center. But its long-range sensor and its own insatiable curiosity had been drawn to a particular star, a star that had held a strange and powerful fascination for humanity for millennia. It was a star that had been known, in different cultures and at different times, as a harbinger of bad tidings, as the decapitated, snake-haired head of the Gorgon Medusa, as a pile of corpses in a celestial mausoleum. It was the demon star, Algol. The change in course would cost Batuta an additional 8,000 years in its overall journey time. But the ancient and deeply human mystery of this star was too compelling to ignore. The strange and eerie behavior of Algol had been noted as far back as ancient Egypt, where a 3,200-year-old papyrus, a calendar of lucky and unlucky days, listed it as a star of ill omen. In the 17th century, the Italian astronomer Geminiano Montanari discovered that the star's ominous reputation was rooted in a real physical phenomenon, its brightness changes. More than a century later, it was found that this change was periodic. Roughly every 3 days, Algol would suddenly dim for a period of about 10 hours, before returning to its normal brightness. The cause of this celestial wink was finally understood in the 19th century. Algol is not a single star, but a binary star system, a close pair of stars orbiting a common center of mass. The dimming occurs when the fainter companion star passes in front of the brighter primary star from our point of view, a celestial event known as an eclipsing binary. But this simple, elegant explanation hid a deeper and more violent story. When astronomers were finally able to measure the properties of the two stars, they found a paradox. The larger, more massive star, Algol A, is a hot, blue, main-sequence star, still in the prime of its life, fusing hydrogen into helium in its core, its smaller, less massive companion. Algol B, however, is a more evolved, subgiant star, a star that has already exhausted the hydrogen in its core and is nearing the end of its life. This is the exact opposite of what stellar evolution theory predicts. More massive stars burn through their fuel much faster than less massive stars. Algol A, being the more massive of the pair, should have been the first to evolve off the main sequence. The solution to this Algol paradox is a process of stellar vampirism. The two stars were indeed born at the same time, and initially Algol B was the more massive of the pair. It therefore evolved faster, and as it reached the end of its main sequence life, it swelled up to become a red giant. Its outer atmosphere expanded so much that it overflowed its Roche lobe, the region of space around a star in a binary system within which material is gravitationally bound to that star. This allowed its smaller, but still gravitationally powerful companion, Algol A, to begin siphoning off the hydrogen from its outer layers, over millions of years, a vast amount of mass was transferred from Algol B to Algol A, reversing their mass ratio and creating the paradoxical configuration we see today. The demon star is a cannibal. Algol is just one of a vast and diverse population of multiple star systems that are now known to be common throughout the galaxy. In fact, it is thought that at least half of all sun-like stars are in binary or multiple systems. These systems come in a dizzying array of configurations, from simple, wide binaries to complex, hierarchical systems of up to 9 stars, all locked in an intricate gravitational dance. Our nearest stellar neighbor, Alpha Centauri, is a triple system with 2 sun-like stars in a close orbit, and a third, small red dwarf, Proxima Centauri, in a much wider and more tenuous orbit around the central pair. The dynamics of these multiple star systems are incredibly complex and often chaotic. They are places of intense gravitational interactions, of stellar collisions, of mass transfer, of planets being flung out into the cold and the dark of interstellar space. They are a reminder that our own single-star solar system, with its stable, orderly, and long-lived environment, may be a relatively rare and fortunate configuration. But multiple star systems are not the only curiosities in our local galactic neighborhood. Just as there are stars of all different sizes and colors, there are also worlds of all different kinds. In the 19th century, the German astronomer Friedrich Bessel, a brilliant, self-taught mathematician who had dropped out of school at the age of 14, was the first person to successfully measure the distance to a star other than our Sun. He did this using the method of parallax, by carefully measuring the tiny, apparent shift in a star's position against the background of more distant stars as the Earth orbits the Sun. The star he chose for this historic measurement was 61 Cygni, a star that was known at the time as the Flying Star because of its unusually large proper motion. Its apparent movement across our sky. Bessel correctly reasoned that this fast apparent motion was a clue that the star was relatively close to us. And when he finally calculated the distance, it was so vast that he had to invent a new unit to describe it, the light year. 61 Cygni, he announced, was a little over 10 light years away, a number that, for the first time, gave humanity a true sense of the immense and almost empty scale of the interstellar void. But 61 Cygni is not the nearest, nor the strangest, star in our sky. That title could go to a star like Betelgeuse, the bright red supergiant that marks the shoulder of the constellation Orion. Despite being over 600 light-years away, Betelgeuse is one of the brightest stars in our night sky. This is because it is a true cosmic behemoth. It is at least 15 times more massive than our Sun, and it is so gigantic that if it were placed at the center of our solar system, its bloated, roiling surface would engulf the orbits of Mercury, Venus, Earth, and Mars, and would reach out into the asteroid belt. Betelgeuse is a dying star, a star in the final, turbulent stages of its life. It is no longer a perfect sphere, but a lumpy, engorged, and violently convective ball of plasma. In late 2019, it unexpectedly and dramatically dimmed, an event that was caused by the star ejecting a massive plume of superheated gas into space, which then cooled and condensed into a cloud of dust, temporarily obscuring our view. Betelgeuse is doomed to explode as a spectacular supernova sometime in the next 100,000 years. When it does, it will be an event of truly epic proportions. It will briefly shine as brightly as the half-moon, a single, brilliant point of light that will be visible in the daytime sky and will be bright enough at night to comfortably read a book by. It will be a stunning and beautiful final act in the life of a true cosmic giant. The vast majority of stars in our galaxy, however, are not giants like Betelgeuse. They are much smaller, much cooler, and much longer lived. They are the red dwarfs, the faint, unassuming, and incredibly numerous population of stars that make up about 75% of the Milky Way's stellar census. Our nearest neighbor, Proxima Centauri, is a typical red dwarf. It is so small and so dim that it is completely invisible to the naked eye, despite being only 4.2 light-years away. But what makes Proxima Centauri remarkable is not the star itself, but what orbits it. In 2016, astronomers announced the discovery of Proxima b, a small, rocky, Earth-sized planet, orbiting within its star's habitable zone, the narrow range of distances where temperatures could be just right for liquid water to exist on a planet's surface. Proxima b is the closest known exoplanet to our solar system, and it is, at present, our nearest, best hope for finding a second, independent genesis of life in the universe. But a planet orbiting a red dwarf would be a very different, and in many ways, a much more challenging place for life to arise. Because red dwarfs are so much cooler than our Sun, their habitable zones are much closer in. Proxima b orbits its star at a distance of only about 7.5 million kilometers, much closer than Mercury orbits our Sun. At this close proximity, the planet is likely to be tidally locked, with one side permanently facing the star in a state of eternal day, and the other side locked in a state of perpetual frozen night. Life, if it exists, would have to cling to a narrow terminator zone, a twilight ring of perpetual dawn and dusk that circles the planet. And red dwarfs are notoriously temperamental stars. They are prone to powerful, violent flares, which can unleash torrents of high-energy radiation and charged particles that would be lethal to any life on an unprotected planet, and could, over time, strip the planet of its atmosphere entirely. Life on a red dwarf planet would be a life lived on the edge, a life of constant struggle against the violent whims of its parent star. And so, the galaxy is a place of almost infinite variety. There are systems with multiple suns and worlds of perpetual twilight. There are giant, dying stars and tiny, smoldering embers. There are planets so close to their stars that their surfaces are molten seas of rock, and rogue planets that have been flung out of their home systems and now wander the cold, dark, and lonely void between the stars, their only source of heat, the slow, radioactive decay of elements in their cores. It is a cosmic zoo of almost unimaginable diversity. And Batuta, after its brief, 10,000-year detour to the demon star, continued its long and patient journey through this zoo. It knew that the true, deep mysteries of the cosmos, the secrets of life, of physics, of the universe's ultimate origins and fate, were not to be found in this quiet, suburban arm of the Milky Way. For that, it would have to travel much further, much deeper, into the fiery, chaotic, and brilliant heart of the galaxy itself. Batuta had set itself a new and deeply ambitious goal to find a way to escape the Milky Way entirely. This was not a task that had been programmed into its original mission parameters. Its human creators, in their wildest dreams, had not imagined a journey beyond the confines of their own home galaxy. But Batuta, after its long and lonely voyage, after its countless encounters with the wonders and the terrors of the cosmos, had evolved. It had developed a new sense of purpose, a new and almost spiritual yearning to see what lay beyond the final cosmic horizon. But to leave the galaxy, it would first have to pass through its most dangerous and most spectacular region, the galactic center. After a journey of nearly 10 million years, a journey that had carried it across thousands of light-years of interstellar space, through the dense, star-forming regions of the Scutum Centaurus arm, Batuta had finally arrived at the outskirts of the galactic core. The sky here was a completely different world. The familiar, sparse scattering of stars of its home system had been replaced by a dense, blazing, and continuous wall of light. The combined glare of billions of stars packed into a region of space only a few thousand light-years across. The galactic core is an elongated, bar-shaped structure, a place of intense star formation, of powerful magnetic fields, and of extreme, chaotic gravitational dynamics. And at its very heart, hidden behind thick, obscuring clouds of gas and dust, lay the ultimate destination of Batuta's galactic pilgrimage, Sagittarius A, the supermassive black hole that sits at the center of the Milky Way. But as it prepared for this final, dangerous leg of its journey, Batuta was reminded that it was not the only sentient, robotic explorer in this vast and ancient galaxy. Somewhere in the Norma Arm, some 5,000 light-years behind it, Batuta's sensitive, long-range radio antennas had detected a faint and distinctly artificial, staccato signal. It was not a pulsar. The spectral signature was wrong. The rhythm was too complex, too structured. It was a signal of the kind that Batuta itself might have created. A message, a greeting. And so, before it plunged into the chaos of the galactic core, Batuta decided to leave a message of its own, a cosmic cairn, a signpost for any other traveler who might one day pass this way. It spent the next 10,000 years carefully and patiently manipulating the orbits of the planets in a long-dead, lifeless star system, causing them to spiral into their parent star. The result was a dramatic and unnatural increase in the star's metallicity, a sudden and anomalous spike in its abundance of heavy elements. It was a signal that would be visible to any sufficiently advanced astronomical survey. For millions of years to come, a quiet and beautiful piece of stellar graffiti, a message that simply said, "I was here." And so now, its message sent, its long journey through the spiral arms complete. Batuta finally turned its attention to the dark, galactic heart. It had spent nearly 10 million years in transit, a timescale that was almost incomprehensible to the short-lived biological beings who had created it. It had seen stars that were almost as old as the universe itself, and it felt, in its own silicon-based way, a sense of its own, growing antiquity. And yet, it knew that its own long life was but a fleeting instant compared to the age of some of the true, ancient denizens of the galaxy, the firstborn stars that had witnessed the cosmic dawn. One of the most famous of these is a star that human astronomers had nicknamed Methuselah, after the biblical patriarch who was said to have lived for 969 years. The star's official designation is HD 140,283, and it is a relatively nearby and unassuming subgiant star. But when astronomers first managed to get a precise measurement of its age, they were shocked. The initial estimates suggested that the star was over 14 billion years old, seemingly older than the universe itself. This was a paradox that threatened to overturn our entire understanding of cosmology. But the solution to the riddle of Methuselah, as is so often the case in astronomy, lay not in a flaw in our theories, but in the uncertainties of our measurements. Estimating the age of a single, isolated star is an incredibly difficult and imprecise science. It relies on a complex and often model-dependent analysis of the star's brightness, its temperature, its chemical composition, and its motion through the galaxy. Later, more refined measurements of Methuselah have brought its age down to a value that is consistent with the age of the universe, albeit with large error bars. There is no doubt that the star is ancient, one of the oldest known stars in our galaxy. But it is not a paradox, and it is not even in all likelihood, one of the true first-generation stars. Methuselah is what astronomers call a population 2 star. This classification scheme, which divides stars into three broad populations based on their age and chemical composition, was first developed in the 1940s by the German-American astronomer Walter Baade. During the Second World War, the city of Los Angeles was subject to a series of strict wartime blackouts designed to protect it from potential nighttime attacks by Japanese submarines. For Baade, who was working at the Mount Wilson Observatory in the hills above the city, this was a scientific opportunity of a lifetime. The reduced light pollution allowed him to take the clearest, deepest images ever made of the neighboring Andromeda galaxy. And in those images, he was able to resolve individual stars and to distinguish between two distinct stellar populations. Population 1 stars, like our own Sun, are relatively young, are found primarily in the disk of the galaxy, and are rich in metals, the astronomical term for any element heavier than hydrogen and helium. Population 2 stars, on the other hand, are ancient, are found primarily in the galaxy's central bulge and its surrounding spherical halo, and are very poor in metals. This distinction tells a beautiful story of cosmic chemical evolution. The very first stars to form in the universe, the hypothetical population 3 stars, were born from the pristine, primordial gas of the Big Bang, a gas that contained only hydrogen and helium. These stars were likely incredibly massive, and they lived short, violent lives, ending in spectacular supernova explosions that forged the first heavy elements and seeded the interstellar medium with them. The next generation of stars, the population 2 stars, like Methuselah, were born from this slightly enriched gas. They have a low, but non-zero, metal content. And they, in turn, through their own stellar life cycles, continued this process of chemical enrichment. And so, with each successive generation, the metal content of the galaxy has increased. Our own population all-wise Sun, born a mere 4.5 billion years ago, is the product of many generations of this cosmic recycling, and its relatively high metal content was the essential prerequisite for the formation of a rocky terrestrial planet like our own. The true firstborn. Population 3 stars have never been directly observed. Their immense mass meant that they burned out and died long ago, in the first few 100 million years of the universe's history. But their light, stretched and redshifted by 13 billion years of cosmic expansion, is still traveling towards us. And the James Webb Space Telescope, with its incredible infrared sensitivity, is now, for the first time, giving us the chance to see it, to capture the faint ancient glow of the cosmic dawn, and to witness the birth of the very first stars. The life cycle of a star is a dramatic story, a story of a long, and often violent, battle between the inward pull of gravity and the outward push of nuclear fusion. The final act of this story depends, almost entirely, on a single parameter, the star's initial mass. The smallest stars, the red dwarfs, are the most frugal of cosmic beings. They sip their hydrogen fuel so slowly that they can live for trillions of years, far longer than the current age of the universe. When they finally do run out of fuel, they will simply, quietly, and gently fade away, becoming cold, dark embers known as black dwarfs. Medium-sized stars, like our Sun, have a much more dramatic fate. When they exhaust the hydrogen in their cores, they will swell up to become enormous red giants. Our own Sun, in about 5 billion years, will expand to engulf the orbits of Mercury and Venus, and will likely boil away the oceans and atmosphere of the Earth. After this red giant phase, the star will shed its outer layers, creating a beautiful, glowing, and short-lived structure known as a planetary nebula. At the center of this nebula will be the star's hot, dense, and slowly cooling core, a white dwarf. A white dwarf is an object of incredible density. It has the mass of a sun, but it has been compressed into a volume the size of the Earth. A single teaspoon of white dwarf material would weigh several tons. It is an object that is no longer powered by nuclear fusion. It is a stellar corpse, supported against the crush of its own gravity by a quantum mechanical phenomenon known as electron degeneracy pressure. The electrons in the white dwarf are packed so tightly together that the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state, creates a powerful outward pressure that halts any further gravitational collapse. But even this powerful quantum pressure has its limits. If a white dwarf is in a close binary system, it can, like Algol, begin to siphon material from its companion star. If it accretes enough mass to push it over a critical limit, the Chandrasekhar limit, which is about 1.4 times the mass of our Sun, the electron degeneracy pressure will no longer be strong enough to support it. The white dwarf will begin to collapse, and this collapse will trigger a runaway thermonuclear explosion that will completely obliterate the star in a cataclysmic event known as a Type Ia supernova. These are the supernovae that are used as standard candles to measure the expansion of the universe. They are events of incredible power, briefly outshining their entire host galaxy. But for the most massive stars, those that are born with more than about 8 times the mass of our Sun, the end is even more spectacular and even more violent. These stars do not end their lives as white dwarfs. They have enough mass to ignite the fusion of heavier and heavier elements in their cores: carbon, oxygen, neon, silicon. But this process cannot go on forever. When the core is finally converted into iron, the nuclear fusion process stops. The fusion of iron does not release energy, it absorbs it. The star has run out of fuel. The outward pressure of radiation ceases, and gravity. The patient, and ultimately victorious enemy, wins. The iron core collapses catastrophically in a fraction of a second, from the size of the Earth to the size of a city. The temperature and density skyrocket. The protons and electrons in the core are squeezed together to form a super-dense ball of neutrons. The rest of the star, which is now in freefall, comes crashing down onto this newly formed, incredibly hard neutron core and bounces off, creating a powerful shock wave that rips through the outer layers of the star, tearing it apart in a titanic explosion known as a core collapse or Type II supernova. This is the event that creates the Crab Nebula, the beautiful expanding remnant of the supernova that was observed by Chinese astronomers in the year 1054. The physics of a core collapse supernova is one of the most complex and extreme phenomena in all of nature. The moment of core bounce, when the infalling material hits the hard neutron core, is not in itself powerful enough to blow the star apart. The shock wave stalls, its energy sapped by the dense, overlying layers of the star. For decades, this was a major puzzle in astrophysics. How do these massive stars actually explode? The answer, we now believe, lies in a tiny, almost massless, and incredibly elusive particle: the neutrino, in the incredible, high-density environment of the collapsing core. A vast number of neutrinos are produced. In fact, over 99% of the immense energy of the supernova is carried away not by the light of the explosion, but by these ghostly, weakly interacting particles. The vast majority of these neutrinos stream out of the star, completely unimpeded. But a small fraction of them, perhaps 1%, are absorbed by the material behind the stalled shock wave. And this tiny fraction is enough. The immense energy of the absorbed neutrinos is what reinvigorates the shock, giving it the powerful outward push it needs to blast through the rest of the star and create the spectacular explosion that we see. The supernova of 1987, a relatively nearby explosion in the Large Magellanic Cloud, gave us our first direct confirmation of this neutrino-driven mechanism. In a deep underground laboratory in Japan, a detector named Kamiokande-2, a vast tank of ultra-pure water surrounded by sensitive light detectors, recorded a brief 12-second-long burst of just 25 neutrinos. These were the first, and so far, only, neutrinos ever detected from a supernova explosion. And they arrived at the Earth a few hours before the light from the explosion, just as the theory predicted, as the neutrinos are able to escape from the dense, collapsing core while the light is still trapped within the expanding fireball. It was a stunning triumph of theoretical and experimental physics, a beautiful confirmation of our understanding of the deep inner workings of a dying star. And as Batuta itself had learned, in a moment of near catastrophic personal experience, these events are not just beautiful, they are also incredibly and unpredictably dangerous. It had been peacefully refueling in what it thought was a stable, long-dead binary system, when one of the white dwarf's companions had unexpectedly gone supernova. The first warning was a sudden, intense burst of neutrinos and gamma rays, just seconds before the main shock wave of the explosion hit, a wave of energy and radiation so powerful that it had almost destroyed the ancient, and now battle-scarred, probe. It had taken Batuta over 1,000 years to repair the damage, to piece itself back together in the tattered, glowing remnants of the destroyed system. And as it did so, licking its wounds, it made a solemn vow. It had grown complacent, overconfident. The galaxy was not a safe, predictable place. It was time to stop its leisurely, sightseeing tour. It was time to face the final, and greatest, challenge of its galactic journey. It was time to go to the heart of the beast, to confront the supermassive black hole at the center of the Milky Way, and then, if it survived, to leave its home galaxy forever. After its long and often perilous journey, a journey that had spanned nearly 10 million years and had carried it across the vast, star-dusted spiral arms of the Milky Way. Batuta had finally arrived. It hung on the edge of the abyss. Its sensors trained on the chaotic, brilliant, and terrifying heart of its own home galaxy. Before it lay Sagittarius A, the monster, a 4 million solar mass supermassive black hole, a silent, dark maw in the very fabric of spacetime. The environment surrounding this beast was a place of unparalleled violence and beauty. The glare of millions of stars, packed into a region only a few light years across, created a celestial city of almost unbearable brightness. Vast clouds of hot, ionized gas swirled in complex, turbulent orbits, their motion dictated by the immense and invisible gravitational pull of the central monster. And from the immediate vicinity of the black hole itself, from the incandescent, swirling accretion disk of matter that was being torn apart and consumed, came a powerful and incessant torrent of radio waves and high-energy radiation. This was the most continuously energetic place in the entire galaxy. And beneath it all, under the maelstrom of plasma, under the flood of radiation, lay the black heart itself, the event horizon, a perfect spherical, one-way membrane, cutting off the interior of the black hole from the rest of the known universe. For a brief and tantalizing moment, Batuta was tempted to take the final plunge, to cross that silent, dark threshold, and to see for itself what lay within. Its creators had died without ever having cracked the riddle of quantum gravity, without a theory that could describe the infinitely dense and infinitely mysterious singularity that lay at the heart of every black hole. The answer was there, hidden in the silent, dark depths of the beast. But it was a trap. Batuta knew that if it were to send itself, or even a small, unmanned probe, across that horizon, it might learn nature's ultimate secret. But it would never be able to return, never be able to tell anyone what it had found. The information would be lost to the outside universe forever. It was a one-way ticket to a place beyond space and time, a place from which no traveler and no message could ever return. The story of our understanding of black holes is a story of a slow and often reluctant acceptance of a reality that seemed, at first, to be a mere mathematical absurdity. The singularities, the points of infinite density and curvature that first appeared in Carl Schwarzschild's pioneering 1916 solution to Einstein's equations, were, for decades, dismissed by most physicists, including Einstein himself, as unphysical artifacts of an oversimplified model. The idea that a real physical object could collapse to a point of zero volume and infinite density seemed a bridge too far, a violation of common sense and physical intuition. But a small minority of physicists, like J. Robert Oppenheimer, took the possibility seriously. And as our understanding of astrophysics and our observational capabilities grew, the evidence began to mount. In the early 1970s, astronomers discovered a powerful and variable source of X-rays in the constellation Cygnus, an object they named Cygnus X1. It was a binary system with a large, bright, blue supergiant star in a close orbit with a smaller, unseen companion. By carefully measuring the orbit of the visible star, astronomers were able to calculate the mass of its invisible partner, and the number they got was a shock. The companion was at least 15 times the mass of our Sun, far too massive to be a white dwarf or a neutron star, and all of this mass was packed into a region of space so small that it could not be resolved by their telescopes. There was only one object that could fit this description: a black hole. It was the first, and still one of the best, observational candidates for a stellar mass black hole. In 1975, Stephen Hawking and Kip Thorne, two of the leading theoretical physicists of their generation, made a famous and playful bet on the existence of Cygnus X1. Hawking, playing the role of the skeptic, bet that it was not a black hole. Thorne, the believer, bet that it was. The stakes were a subscription to a magazine. In 1990, after the evidence had become overwhelming, Hawking conceded the bet. The era of black hole astronomy had truly begun. We now know that our universe is littered with these strange and wonderful objects. We have found stellar mass black holes, the remnants of massive stars, with masses ranging from a few to a few dozen times that of our Sun. And we have found the true giants, the supermassive black holes that lie at the centers of most, if not all, large galaxies, with masses ranging from millions to billions of times that of our Sun. In 2019, the Event Horizon Telescope, a global network of radio telescopes that effectively creates a virtual telescope the size of the Earth, gave us our first direct image of one of these beasts, the shadow of the 6.5 billion solar mass black hole at the center of the giant elliptical galaxy Messier 87. The physics of a black hole is a physics of extremes. The gravitational pull at its event horizon is so strong that the escape velocity, the speed you would need to escape its gravitational pull, is equal to the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. The horizon is not a physical surface. It is a point of no return, a one-way door in spacetime. If you were to fall into a small stellar mass black hole, the tidal forces, The difference in the gravitational pull on your head and your feet would be so strong that you would be stretched into a long, thin strand of atoms, a process of spaghettification, long before you ever reach the horizon. But for a supermassive black hole, like Sagittarius A, the horizon is much further out from the singularity, and the tidal forces there are much gentler. You could, in principle, cross the event horizon of a supermassive black hole without even noticing. You would be in free fall, and you would feel no forces. The universe outside would still be visible to you, but you would have passed the point of no return. Your fate would be sealed. Outside the event horizon, you are free to move in any direction in space, but you are compelled to move forward in time. Inside the event horizon, a strange and terrible reversal occurs. The roles of space and time are, in a sense, interchanged. The singularity, the single point at the center of the black hole, is no longer a place in space. It is a moment in your future. It is an unavoidable future moment of time. You can no more avoid hitting the singularity than you can avoid next Tuesday. All paths, all possible future world lines, lead to the center. For a black hole the size of Sagittarius A, the time it would take to travel from the event horizon to the singularity, as measured by a watch on your wrist, would be about 20 seconds. What you would experience at the singularity itself is a question that our current physics cannot answer. General relativity predicts a point of infinite density and infinite spacetime curvature, a place where the laws of physics break down. A full theory of quantum gravity is needed to understand what truly happens at the heart of a black hole. But whatever the ultimate nature of the singularity, the journey's end would be a final and absolute obliteration. And so, Batuta, for all its curiosity, knew that this was a journey it could not take. Its mission was to return, to report, to save its creators. And so, it prepared for the most difficult and most dangerous navigational maneuver of its long and storied life. It would not plunge into the abyss, it would skim it. It would use the immense, rotating gravitational field of the supermassive black hole as a cosmic slingshot, a process known as the Penrose process. It would dive in close, into the ergosphere, a region just outside the event horizon where space-time itself is being dragged around by the black hole's rotation. There, it would jettison a carefully calculated amount of mass, dropping it into the black hole in such a way that it would steal a tiny fraction of the black hole's rotational energy and add it to its own. It was a maneuver of incredible precision, a dance on the very edge of oblivion. A single, tiny miscalculation would send the probe spiraling into the event horizon, its long journey ending in a final, silent scream. But Batuta, after its 10 million years of practice, was a master of celestial mechanics. At just the right moment, as it grazed the very edge of the ergosphere, it fired its engines, altered its course by a barely perceptible, infinitesimal amount, and was flung out, away from the black hole, propelled by the stolen energy of the spinning giant on a new trajectory, at a substantial fraction of the speed of light, a trajectory that would take it up out of the plane of the Milky Way, and into the vast, dark, and unknown expanse of intergalactic space. It had survived. It had escaped. After a journey of 40 million years, a journey that had carried it across the 2.5 million light-year gulf between the Milky Way and its great spiral neighbor, Andromeda, Batuta felt a new and unfamiliar emotion. It was loneliness. For 40 million years, it had sailed through an almost perfect void, a vast cosmic desert of near-perfect emptiness. The grand familiar and star-dusted spiral of its home galaxy had shrunk behind it, becoming a faint, beautiful, and ultimately insignificant smudge of light. and the great, majestic spiral of Andromeda had grown before it. 1 trillion stars. A new and unexplored continent of cosmic possibility. The space between the galaxies is not entirely empty. It is filled with a thin, tenuous, and incredibly hot plasma. The warm-hot intergalactic medium, or WIM, this gas, mostly hydrogen and helium, is thought to be the leftover primordial material that never managed to collapse into galaxies, and it may, in fact, contain up to half of all the normal baryonic matter in the universe. But it is a substance of almost unimaginable thinness, with only a few atoms per cubic meter. It is a ghost of a medium, a near-perfect vacuum by any terrestrial standard. And as Batuta glided through this silent, empty expanse, it had a lot of time to think. It had time to process the vast amounts of data it had collected, to reflect on its long and eventful journey, and to consider its ultimate mission to find a path to salvation for the fragile, biological beings who had created it. And it was this mission that had brought it here, to Andromeda, a galaxy that was larger, more massive, and in many ways more violent and more energetic than its own familiar Milky Way. It was here that it hoped to find the most extreme objects, the most powerful events, the new and exotic physics that might hold the key to transcending the immense and seemingly insurmountable barriers of interstellar, and now intergalactic travel. And after several hundred years of patient, long-range observation, as it approached the outskirts of the Andromeda galaxy, Batuta found its first and most compelling candidate. It was a strange and powerful stellar remnant, an object that was a testament to the fact that even in death, a star can be a thing of terrible and beautiful power. The story of this object begins, as so many stories in astronomy do, with a graduate student, a late night, and a puzzling, anomalous signal. In 1967, Jocelyn Bell, a PhD student at the University of Cambridge, was poring over the long paper printouts from a new radio telescope she had helped to build. Her job was to look for the faint, twinkling signals of quasars. But one night, she noticed something else. A strange, repeating signal. A bit of scruff, as she called it. That did not look like a quasar, or like any known form of radio interference. It was a series of perfectly regular pulses, repeating every 1.337 seconds, with a precision that was almost unnatural. Her supervisor, Anthony Hewish, was initially skeptical, but Bell was persistent, and they were eventually able to confirm that the signal was real, and that it was coming from a fixed point in the sky. Jokingly, they nicknamed the source LGM-1 for Little Green Men, but they soon found other similar signals from other parts of the sky, and it became clear that they had stumbled upon a new and natural class of astrophysical object. The explanation, when it came, was not a new invention, but the revival of a brilliant and largely forgotten idea from the 1930s. The astronomers Walter Baade and Fritz Zwicky had predicted that the end result of a core collapse supernova would be an incredibly dense, city-sized ball of almost pure neutrons, a neutron star. And it was quickly realized that if a neutron star were rapidly rotating and had a strong magnetic field, it could act like a cosmic lighthouse, its magnetic poles sweeping out to powerful beams of radio waves that, if they happened to cross our line of sight, would be observed as a series of regular pulses. The pulsar was born. Anthony Hewish would go on to win the Nobel Prize in Physics for his role in the discovery. Jocelyn Bell, the graduate student who had first noticed the signal and had argued for its significance against the skepticism of her supervisor, was, controversially, not included in the prize, but her name will forever be associated with one of the great serendipitous discoveries in the history of astronomy. Neutron stars are objects of almost unimaginable extremity. They are the densest form of matter known in the universe, just one step away from collapsing into a black hole. A single teaspoon of neutron star material would weigh billions of tons. Their gravitational pull is so strong that the tallest mountains on their surfaces are only a few millimeters high. And they spin with incredible speed. The conservation of angular momentum from their progenitor stars collapse, whipping them into a frenzy. The fastest known pulsar rotates 716 times every second, its surface moving at a significant fraction of the speed of light. But some neutron stars are even more extreme. They are the magnetars. These are young neutron stars that are born with or develop magnetic fields that are 1,000 times stronger than those of a normal pulsar, and a quadrillion times stronger than the magnetic field of the Earth. These are the strongest magnetic fields known in the universe. The energy stored in this magnetic field is so immense that it can cause the solid crust of the neutron star to crack and shift, triggering a starquake. These starquakes can release a tremendous amount of energy in a sudden, violent burst of X-rays and gamma rays, a flare that can be so powerful that it can be detected from across the galaxy. It was just such a flare. From a distant magnetar in the Andromeda Galaxy, that Batuta had detected a flare so powerful that it had temporarily overwhelmed its sensors. The spacecraft, for all it had seen, was not easily impressed. But the sheer, raw, and untamed power of the magnetar was a thing of true and terrible wonder. It was a reminder that the universe is a place of extremes, a place where the laws of physics are pushed to their absolute limits. But even the wrath of a magnetar, Batuta was about to learn, was not the most powerful or the most mysterious event that the cosmos had to offer. The explosion that had emanated from the magnetar's surface had been a surprise, a sudden and violent outburst that had temporarily blinded Batuta's sensors and had served as a stark reminder of the unpredictable and often ferocious nature of the cosmos. But as the spacecraft recovered, and as it analyzed the data from the event, it realized that it had stumbled upon a crucial clue in a long-standing astronomical mystery. The burst of gamma rays from the magnetar was a powerful event, but it was a relatively soft and short-lived one. For decades, astronomers had been aware of another, far more powerful and far more enigmatic class of cosmic explosions, the gamma-ray bursts, or GRBs. The story of their discovery is a strange and serendipitous one, a tale of Cold War paranoia and a secret, space-based nuclear surveillance program. In 1963, the United States and the Soviet Union signed the Partial Nuclear Test Ban Treaty, which prohibited the testing of nuclear weapons in the atmosphere, in outer space, and underwater. But the U.S. military, ever suspicious of its Soviet counterparts, worried that the Soviets might try to cheat by conducting secret nuclear tests on the far side of the moon. And so, they launched the Vela satellites, a fleet of spacecraft placed in a high orbit, far above the Earth's radiation belts, equipped with sensitive gamma-ray detectors designed to spot the telltale flash of a clandestine nuclear explosion. The Vela satellites never did detect any secret Soviet nuclear tests. But starting in 1967, they did begin to detect something else brief, intense, and completely inexplicable bursts of gamma rays, coming not from the Earth or the Moon, but from random directions in deep space. The data was classified, and for years, the existence of these cosmic fireballs was a closely guarded military secret. It was not until 1973 that the information was finally declassified and released to the scientific community, and the puzzle of the gamma-ray bursts was born. We now know that GRBs are the most luminous electromagnetic events known to occur in the universe. A typical GRB can release as much energy in a few seconds as our Sun will in its entire 10 billion year lifetime. They come in two main flavors: short GRBs, which last for less than 2 seconds, and long GRBs, which can last for several minutes or even hours. The short GRBs are now understood to be the product of one of the most violent events imaginable, the merger of two neutron stars. As these two incredibly dense stellar corpses spiral into each other, they release a tremendous amount of energy, not just in the form of gravitational waves, but also in a highly collimated, relativistic jet of particles that produces a brief, intense flash of gamma rays. In 2017, we witnessed this process directly for the first time when the LIGO and Virgo gravitational wave detectors recorded the signal of a neutron star merger. And just a few seconds later, the Fermi Gamma Ray Space Telescope detected a short GRB from the same patch of sky. It was a stunning triumph of multi-messenger astronomy, a beautiful confirmation of our theoretical models. The origin of the long GRBs, however, has been a more enduring mystery. They are known to be associated with the deaths of very massive stars, as they are almost always found in distant, star-forming galaxies. The leading model is the collapsar model. In this scenario, a very massive, rapidly rotating star, at the end of its life, collapses to form a black hole. But because of its rapid rotation, the material of the star does not all fall directly into the black hole. Instead, it forms a dense, hot, and rapidly rotating accretion disk around the newborn black hole. The complex interplay of magnetic fields and frame dragging in this extreme environment can then launch two incredibly powerful and highly collimated jets of plasma, which travel outwards at nearly the speed of light. These jets punch their way through the collapsing star's outer layers, and when they finally break out into interstellar space, they produce the intense and long-lasting burst of gamma rays that we observe. A long GRB is, in this picture, the birth cry of a black hole. But there is another, even more exotic, and even more powerful possibility. For the very most massive stars in the universe, stars with more than 130 times the mass of our Sun, the end can be even more spectacular. In the incredibly hot and dense cores of these supergiants, the gamma-ray radiation can be so intense that the photons themselves can spontaneously transform into pairs of electrons and positrons. This pair instability process robs the star of the radiation pressure that is supporting it against gravity, triggering a runaway thermonuclear explosion that completely obliterates the star, leaving no remnant behind. Not even a black hole. This pair instability supernova is a theoretical prediction, and it is thought to be the most powerful type of stellar explosion in the universe, a hypernova. And it is a leading candidate for the engine behind some of the longest and most luminous gamma-ray bursts. And it was just such an event, a hypernova of almost unimaginable power. That was the likely source of the single, anomalous particle that Batuta had detected millions of years ago. The particle that had set it on its long and lonely journey from Andromeda to the Virgo cluster. The particle was a proton that had been accelerated to an incredible energy, an energy of over 10 to the power of 22 electron volts. This is 100 times more energetic than the famous "Oh my God" particle, the most energetic cosmic ray ever detected by humanity. A particle with this much energy is traveling at a speed so close to the speed of light that the entire 14 billion-year history of the universe would, from its perspective, pass in a fraction of a second. The only known objects in the universe that could possibly accelerate a particle to such a ludicrous speed are the relativistic jets of a gamma-ray burst. But there was a problem. All the known GRBs are incredibly far away, billions of light years from us, and a high-energy cosmic ray, as it travels through the vast intergalactic void, is not traveling through a perfect vacuum. It is constantly colliding with the low-energy photons of the cosmic microwave background. These collisions slowly sap the cosmic ray's energy, a process known as the GZK cutoff. This limits the distance that an ultra-high energy cosmic ray can travel to about 160 million light-years. The fact that we have detected particles with energies above this cutoff is a major puzzle in astrophysics. It suggests that there must be sources of these particles that are relatively nearby, within our local supercluster of galaxies. And Batuta, by painstakingly tracing the trajectory of its own anomalous particle back through the tangled magnetic fields of intergalactic space, had found its source, the giant elliptical galaxy Messier 87 at the heart of the Virgo cluster, some 54 million light-years away. And so, after its long and lonely journey, a journey that had spanned hundreds of millions of years, Batuta finally arrived at its destination. The M87 galaxy is a true cosmic behemoth, a sprawling, ancient city of several trillion stars. And at its heart lies one of the most massive and most active supermassive black holes known in the universe, an object with a mass of 6.5 billion suns. The Event Horizon Telescope had given humanity its first blurry image of this monster, but Batuta was about to get a much closer and much more personal look. It was here, in the chaotic, violent, and brilliant heart of this giant galaxy, that it hoped to find the engine of the universe's most powerful explosions, and perhaps the key to its own long and seemingly impossible mission. After its long and arduous journey across the vast intergalactic void, Batuta had finally arrived at the heart of the Virgo cluster, at the gates of the giant elliptical galaxy Messier 87. And it was here, in this ancient and sprawling city of trillions of stars, that it hoped to find the source of the mysterious ultra-high energy cosmic ray that had set it on this long and lonely pilgrimage. But as it began its survey of the galaxy, it was once again confronted with the sheer, overwhelming scale and complexity of the cosmos. The universe is not just a collection of stars and planets. It is a nested, hierarchical structure of almost unimaginable proportions. Stars are organized into galaxies. Galaxies are organized into groups and clusters are organized into superclusters, vast, interconnected filaments and walls of galaxies that stretch for hundreds of millions of light-years, separated by immense and almost empty cosmic voids. This is the cosmic web, the largest and most magnificent pattern in all of nature, and it is a structure that has been built slowly and patiently over the entire 14 billion-year history of the universe by the gentle but relentless pull of gravity. The story of the cosmic web is the story of gravitational instability. The universe began in a state of almost perfect uniformity, a smooth, hot, and dense soup of matter and radiation. But it was not perfectly smooth. There were tiny, microscopic quantum fluctuations, which, as we have seen, were stretched to macroscopic scales by the process of cosmic inflation. These tiny, primordial seeds of structure were the starting point for everything that was to come. Regions of space that had slightly more matter than average had a slightly stronger gravitational pull. They began to attract more matter from their surroundings, growing ever denser, and regions that had slightly less matter than average became even more underdense, their matter being siphoned off into the growing clumps. It is a process of the rich getting richer and the poor getting poorer. A process of runaway, gravitational collapse that has, over billions of years, transformed the initial to smooth universe into the lumpy, structured, and beautiful cosmic web we see today. The first objects to form were small, dwarf galaxies. These then merged and collided to form larger galaxies, like our own Milky Way, and galaxies, in turn, were drawn together by their mutual gravity to form groups and clusters. The Virgo cluster, the destination of Batuta's long journey, is one of the closest and most well-studied of these cosmic metropolises. It is a dense and dynamic environment, containing over 1,000 galaxies, all orbiting a common center of mass, all interacting with each other in a complex and often violent gravitational dance. And at the very heart of this cluster, dominating its gravitational landscape, lies the giant elliptical galaxy Messier 87. Elliptical galaxies, like M87, are thought to be the end product of a long history of galactic mergers. They are the red and dead giants of the cosmos, ancient cities that have exhausted most of their gas and have largely ceased to form new stars, their light dominated by an old and fading population of red stars. They are the graveyards of the universe, but they are also its most massive and most majestic structures. The cosmic web is not just a static structure, it is a dynamic, evolving ecosystem. The superclusters are the great continental landmasses of the cosmos, and they are not yet fully formed. The clusters and groups that make them up are still, at this very moment, falling towards each other, drawn together by their mutual gravity. Our own Milky Way is part of the local group of galaxies, a small, provincial collection of about 50 galaxies. And the local group is, in turn, part of the Virgo supercluster, a vast and ragged collection of hundreds of groups and clusters, all of which are currently on a long, slow journey towards the Virgo cluster at its heart. And even the Virgo supercluster is just one small part of an even grander structure, a supercluster of superclusters that astronomers have named Laniakea, a Hawaiian word that means immeasurable heaven. Laniakea is a truly immense structure containing over 100,000 galaxies and stretching for over 500 million light-years. And it is just one of many such structures that make up the vast, interconnected network of the cosmic web. And between and among these great cosmic continents lie the vast, empty oceans of the cosmic voids. These are the most underdense regions of the universe. Vast deserts of space-time that can be hundreds of millions of light-years across. The largest of these is the Botez Void, a colossal and almost perfectly empty region of space that is sometimes called the Great Nothing. These voids are not just passive gaps in the cosmic web, they are an active and essential part of its structure. They are the places from which the matter that built the great superclusters was drawn. The grand, shining cities of the cosmos owe their existence to the dark, empty quarries that lie between them. And it was in one of these voids, the Botez Void, that Batuta, according to the information it had received from its alien counterpart, would find the answer to its long and seemingly impossible quest. The idea was almost too strange to contemplate. The source of the universe's most powerful particles, a new and exotic form of physics, was not to be found in the dense, chaotic, and energetic heart of a giant galaxy, but in the coldest, darkest, and most empty place imaginable. But the clue, a complex and beautiful piece of mathematics that had been shared by its alien friend, was compelling. It was a prediction from a theory that was far beyond anything its human creators had ever conceived. A theory that seemed to be a true, unified theory of quantum gravity. And this theory predicted the existence of something truly bizarre, something that should not exist in our universe, something that was a leftover, a fossil, from the very first and most violent moments of creation, a cosmic string. And so, Batuta, after its long and patient survey of the Virgo cluster and after a final, long and lonely journey across the vast and seemingly empty expanse of the Botez Void, finally found what it was looking for. It was a ghost, a barely perceptible, one-dimensional flaw in the very fabric of space-time. It was a cosmic string. The theory that predicts the existence of such objects is a deep and complex one. It is rooted in the idea that the early universe, as it cooled after the Big Bang, went through a series of phase transitions, similar to the way that water freezes into ice. In these phase transitions, the fundamental forces of nature, which are thought to have been unified into a single, symmetric force at very high energies, froze out and separated from each other. And just as defects, like cracks and dislocations, can form in a crystal of ice as it freezes, it is thought that topological defects could have formed in the fabric of spacetime during these cosmic phase transitions. A cosmic string is the simplest of these defects. It is a one-dimensional line of false vacuum, a trapped remnant of the high energy, symmetric state of the early universe. It is an object of almost unimaginable properties. It would have a width that is smaller than a single proton, but a length that could stretch across the entire observable universe. It would have no mass in the conventional sense, as it is made of nothing but a flaw in the vacuum, but its immense energy density, a consequence of the trapped, high-energy vacuum, would give it an effective mass, a gravitational pull. A single kilometer of cosmic string would weigh more than the entire planet Earth. And it would not be static. It would be constantly writhing and vibrating, the ripples on its surface traveling at the speed of light, releasing a torrent of gravitational waves as it did so. The initial calculations of this grand unified theory era of the early universe predicted that our cosmos should be littered with these cosmic strings, but we have never seen one. The fact that we do not see their powerful gravitational lensing effects on the cosmic microwave background has placed very strong limits on how many of them could exist. This has been a major puzzle in cosmology. And it is what led Alan Guth, in part, to invent the theory of cosmic inflation. Inflation, by stretching the universe by an immense factor, would have diluted the density of any cosmic strings that were formed, pushing them far beyond our observable horizon and explaining why our universe appears to be so clean and free of these ancient, monstrous defects. But what if a few of them did survive? What if, by some fluke of the inflationary process, a single, lonely cosmic string was left behind in our observable universe? A single, ancient fossil from the first, fiery moments of creation. And what if this string had been slowly and quietly decaying for the last 13 billion years? Its vibrations releasing not just gravitational waves, but also a steady stream of the most energetic particles in the universe. This was the radical and beautiful idea that had been shared with Batuta. The cosmic string was not just a theoretical curiosity. It was a real physical object, a cosmic particle accelerator of almost infinite power. And it was here, in the deep, dark, and silent heart of the Bowoda's void. Batuta beheld the cosmic string in all its strange and almost terrifying glory. It was a shimmering, ghostly line, stretching for millions of light years in either direction. Its presence revealed only by the subtle and beautiful way it was bending and duplicating the light of the few, faint and distant background galaxies. It was a vision of the beginning of time itself, and Batuta knew, with a certainty that was both exhilarating and deeply frightening, that it had found the answer. It had found the new physics, the new source of energy, the new path to the stars. The details would take centuries, perhaps millennia, to work out. But the principle was clear. A cosmic string was not just a flaw in space-time. It was a gateway. Its extreme energy density, its connection to the physics of the unified forces, its potential link to other hidden dimensions of reality. All of these were a signpost, a clue, a piece of a much larger and much deeper puzzle. The journey had been long, the sacrifices had been great, but the prize was beyond measure. It was the knowledge that could save humanity. And so, the ancient, and now profoundly transformed, probe made its final preparations. It began to shed its non-essential components, its auxiliary sensors, its long-range communication arrays, its now depleted fuel reserves, trimming itself down to its bare essential core, its powerful quantum-entangled communication system, its deep, and now almost infinitely rich, memory banks, and the core of its own, sentient, and now very, very old, artificial intelligence. It then turned to face the nearest section of the shimmering, ghostly string, and it began to accelerate. As it drew closer, it noticed, with a strange sense of amusement, that it felt almost giddy. Its motion effortless, as if the bizarre, paradoxical object before it was not just warping space-time, but was somehow negating its very inertia. It plunged forward, and in a single, silent, and brilliant flash, it slipped into the darkness. Its final thought, as it crossed the threshold into the unknown, was of the man who had, so many billions of years ago, set its distant, robotic ancestors on their own, lonely journey. Far from home, Carl Sagan had written, untouched by these remote events, the Voyagers, bearing the memories of a world that is no more, will fly on. And as Batuta flew on, into the heart of a cosmic string, into a reality beyond the bounds of known physics, it sent its final message back across the vast, and now, not so empty, expansive space, a message that carried with it not just the story of its own epic journey, but the last, best, and only hope for the future of the small and very fragile species that had so long ago dared to dream of the stars.